room, which hopefully will sustain us during a very hot day. Welcome to the final session, final plenary kind of conference of Sprint. It's been an amazing journey. It's a project with so much to share and so much to tell you about. So we're not going to delay just at the moment about that. We're just going to do some practical housekeeping and introduce you to what's going to happen to the day. So my name's Matt Reed. I'm from the University of Gloucestershire. I've been involved with Sprint from the beginning. So I'm just going to moderate for the day. We have a jam-packed session. And so there's lots of people. There's going to be lots of information for you. You should have all of in your note kind of folder here. You'll have lots of other information, including the magazine, which will direct you to more things. So let's just think about some very boring practical things before we get going. There isn't a fire drill. Nobody's mentioned a fire drill to me, but the fire exits are over there, and over there. Try not to post on social media until you get out of the building, please. Just secure yourself. If you're at home online, I don't know where your fire exits are, so you're on your own. So we have, obviously, everybody you can see around you and more people arriving, because I understand there are some public transport problems today. So people are running and cycling across Brussels to be with us. But we have hundreds of people joining us online. So they're very welcome as well. And we will try and include everybody, those online and everybody here, in a degree of participation today. Around the room are lots of people who are helping me. Obviously, we have the local AV tech guys who are making sure that we can all see and hear. We have Paula and Vera on the social media at the back. We have Amanda, who is our illustrator, and you'll see some live illustrations appear behind us. So there will be actual pictures as we go. And so please check in with Amanda. At the back, there is a poster competition. So we have posters from the project, so please check in with those. Jane at the front is doing timekeeping and is also the boss. So just watch out for Jane there, making sure we're on time. And Caitlin, who is just running around and is here to help as well. So we've got lots of people here making all of this work for you. So let's just have a little reminder also that we are recording this. So those of you who don't want to be recorded, if you're online, obviously just hide your face by turning your camera off. If you don't want to be recorded and you're here, let us know and we will erase your face, obviously not literally, but later on the video. So please do let us know. But if you are not on stage, you are not on camera. That would be the other clue. If you're, I don't know, hiding from your boss, hiding from a former partner. Obviously, if you're hiding from the police, just give yourselves up, all right? It'll save a lot of trouble later. So let's just start quickly and have a look at the agenda. So just to show you where we're going this morning, once I'm dragged off stage, we have some distinguished speakers who are going to introduce the project and introduce where we're going. We're going to move to an overview of the project, the policy context, and then we'll move into some results. We'll have chance for a Q&A, and then we'll have a much welcome cup of coffee. And after that quick break, we will carry on with the results, because as you are already beginning to notice, there is a lot to Sprint. There's a lot of different aspects to Sprint, a lot of different things to know and learn about. Then we will come into some policy recommendations. We'll have a great panel discussion with people of all sorts of different persuasions. And then we will have lunch and your chance to take part in the poster session. So that's the morning. I'm not going to bombard you immediately with the afternoon, but the afternoon is similarly jam-packed. So all of the speakers, I'm just looking at you to make sure that you're all on time. Okay, so we all need to be nice and tight on time. But first of all, I'd like to show you all a video that sort of summarizes Sprint. So I'm just looking across. It's going to appear in a moment.
Funded Sprint project investigated pesticide exposure across Europe, and based on our results, we are concerned that EU assessments might underestimate the real-world health and risks of pesticides, particularly from mixtures and long-term exposure. Our study reveals that pesticides are widespread across the environment. We found between 78 and 115 different different pesticide substances in the air, crops, soil, sediments, and fresh waters. Some concentrations in fresh water were above acceptable thresholds set by the EU. Several detected compounds are currently banned in the EU, for example DDE, a persistent toxic breakdown product of DDT. Of all the types of samples tested, indoor dust had the highest variety of pesticide residues. On average, more were found in homes of conventional farmers than in organic farmers' households. These chemicals persist longer indoors because they degrade slowly in dry, dark conditions. About 43% of these pesticides are linked to serious health issues like cancer and hormone disruption. Although individual pesticide levels are below current regulatory safe limits, the combined effects of these chemicals remain uncertain. We also investigated human exposure to pesticides by giving participants wristbands that track their direct contact with chemicals in the environment. Across all wristbands, we found 173 of 191 pesticides, with varying amounts detected in wristbands from conventional and organic farmers, neighbors, and consumers. To assess humans' actual intake of pesticides, we analyzed blood, urine, and feces. We found 90 pesticides overall, with many of these human samples containing multiple compounds. Our research further shows that some pesticides can disrupt the gut microbiome, an effect not considered in standard regulatory tests for pesticides. Our results indicate that current assessments may underestimate real-world risks, especially when pesticides are in mixtures where they potentially act together to increase each other's toxicity. We have developed a practical toolbox to support improvements to pesticide risk assessment, with information on real-life mixtures and expanding surveillance to human biomonitoring for a more comprehensive exposure assessment. To reduce society's reliance on pesticides, we need sustainable, affordable alternatives. Our success stories from across Europe show that change is possible and help shape our recommendations for policymakers. To learn more, visit our website for resources.
Great, thank you very much. Hopefully that gives you a little taster of the scope and depth of Sprint, that there's a lot to think about and a lot to discuss. There may be things that are new to you. I'm always struck by the rubber bands on the wrist as an incredibly simple way of collecting samples, but very effective. So we will recap and we'll go through in detail today most of this. And for those of you who want to review that again, of course, that will be made available online, so you can look at that in the future. So we've done the video premiere. So the next bit, we're going to come to our first set of speakers. So if I could just invite them to the podium. How do we describe the stage? Let's call it a stage. So please, Gisela and Isabelle, please. And then we have Yann online, I'm hoping. Is that correct? Yeah, okay, please. Right, so just welcome to the stage Gisela Quaglia, who's from DG AGRI, who's been with the project from the beginning. We have Yann Devos, who will appear online, who's from the European Food Safety Agency, and Isabelle Baldi, who's a professor of environmental and occupational health at the University of Bordeaux. Gisela, please.
So good morning, everyone. It's a real pleasure to join you today for this important event. I would like to thank Sprint for a project for this kind of invitation. On behalf of DG AGRI, I'm pleased to share opening remarks on why research and innovation are key to shaping the future of sustainable plant protection. At a time when European agriculture is facing unprecedented challenges, from climate change and biodiversity loss to evolving pest pressure, soil degradation, and changing societal expectations, our commitment to science-based innovative solutions have never been more important. Through the EU flagship research program, Horizon 2020 and Horizon Europe, we are making long-term strategic investments to address these challenges. Under Horizon Europe, nearly 9 billion euros were allocated in Cluster 6 for research and innovation in the areas of agriculture, food, bioeconomy, environment, and natural resources. Around 30% of this budget directly support projects in agriculture, forestry, and rural areas, including many targeting plant health and crop protection. These investments are already generating new tools for prevention, monitoring, and control of pests and diseases. Importantly, they also support the development of safer, more sustainable alternatives to harmful pesticides, from biological solutions to agroecological approaches, helping farmers manage pests more sustainably. But innovation doesn't stop at the lab. The real impact comes when this knowledge is transferred into cost-effective, viable practice on the ground through advisory networks, demonstration, and farmer involvement. That's the bridge we are building. This aligns with the vision for agriculture and food presented by the Commission in February, which calls for future-proofing the agri-food sector and highlights the importance of giving farmers better tools to protect crops while reducing environmental impacts. We support holistic systemic transition through initiatives like the EU Mission A Soil Deal for Europe and the co-funded agroecology partnership. These initiatives recognize that one-size-fits-all solutions do not work in agriculture, in particular in plant protection. Instead, we promote place-based innovation through living labs and lighthouses, fostering locally adapted practices that are developed and tested with farmers. The agroecology partnership, launched in January last year, is a major step forward. It backs context-specific, co-created research and innovation across the EU, supporting crop protection, soil health, biodiversity, and more. The partnership involves several EU member states and countries associated with Horizon Europe, and it will enhance the knowledge base and provide solutions and tools to underpin Europe's agroecology transition. The partnership will, among others, explore how agroecology can become the key instrument to reduce the use of pesticides in agriculture and to maximize the contribution of farming to biodiversity protection and nature restoration. Let me turn to the Common Agriculture Policy. Today, knowledge and innovation is a cross-cutting objective of all CAP strategic plans. Through farm advisory services and strengths acquis, we ensure that innovation reaches farmers quickly and effectively. The CAP also supports bottom-up innovation through the European Innovation Partnership, EIP AGRI. Since 2014, around 4,000 operational groups have been launched, and about 600 of those focus on pest and disease control. These are collaborative, farmer-driven projects that deliver real solutions on the ground. One standout example is the Colorado beetle catcher, an eco-innovative machine developed by Dutch farmers and technicians. It has significantly reduced the need for pesticide in potatoes, and now is being adapted for other crops across Europe. We invest as well in innovation for alternative solutions. Projects like Sagropia and NextGen Biopest are advancing biological and low-risk control methods, integrating them into practical integrated pest management strategies. The development of alternatives has been a high priority for several years already. As a result, related actions have been programmed beyond Cluster 6, including in Cluster 4, in Pillar 3 under the European Innovation Council, the Circular Bio-Based Europe Joint Undertaking, and most recently, the Soil Mission Work Programme. 3 ongoing Horizon Europe projects, Good, AgroSUS, and Conserva, are at the forefront of advancing agroecological approaches to weed management, promoting sustainability and reduced reliance on herbicides, for example. Initiatives like Renovate and Advisory Net Pest are reinforcing training and advisory system for crop protection, ensuring innovations are transferred, tested, and scaled up. From the 7th framework program through Horizon 2020 to Horizon Europe, the EU has consistently doubled down on plant protection research and innovation. We have introduced new tools and instruments, as I mentioned, from the multi-actor approach to EU missions to co-funded partnerships to ensure that research is conducted with farmers, not just for them. I would like to close by emphasizing that research, innovation, and knowledge sharings are essential tools for shaping the future of agriculture. This was highlighted in the vision for agriculture and food as well. We will hear today about spring results. These insights are critical as we work together to reduce pesticide use and risk, to improve resilience and safeguard health and the environment. Thank you to the Spring Consortium for your hard work. I wish you all a fruitful, engaging conference and look forward to the discussion ahead.
Okay, so Yann is joining us online. So fingers crossed, how are we doing?
I hope you hear me. Do you? You see the slides and you hear me or not?
We can hear you.
Okay, perfect. Thank you very much. No, first of all, a big thank you for the invitation. So we are very grateful.
Hold on a minute. Hold on, Matt. Yeah, we can hear you, but I don't. Can we see his slides? Okay, we're all good. Okay, thank you. Please continue.
Thank you. No, many thanks for the invitation and apologies for not being able to join you in person. So we are grateful to be able to give you an update on EFSA's considerations about Sprint online. So many thanks for that. You will see several colleagues contributed to the presentation, and the idea is to reflect on why Sprint matters. So I work for the European Food Safety Authority. Our mission is to provide scientific advice to EU risk managers on food safety. We communicate that advice, and also we can't do our work alone because issues are very complex, so we promote scientific cooperation to work together on those aspects. The challenge is that we operate in a fast-changing world. Like today, for instance, we will be exposed to new scientific evidence. So it's important that that evidence is also considered in EFSA's futures risk assessments. So we need to keep up with the latest scientific developments, so to make sure that the risk assessments remain fit for purpose. In EFSA's remit, I mean, the goal is to protect animal health, human health, the health of plants, but also the environment. And we do that by providing scientific advice. You will see that we address several types of stressors. One of those is pesticides and also mixtures to some extent. The main question is, what type of strategic alignment is there between EFSA and Sprint or any other research-funded project? I mean, one of the big alignments is the support to the One Health goals, which is an important one. And then also we note that Sprint has the ambition to provide tools and data for regulatory risk assessment science. In terms of the One Health, you know, we operate in a fragmented regulatory context. Therefore, EFSA is keen to support the One Health agenda in Europe as much as possible. So we are working on that, and there is a lot of research that needs to be done to achieve that goal. So we need to expand the One Health knowledge, promote more transdisciplinary scientific research, and also make sure that we move towards more cross-sectoral scientific advice. And in that respect, Sprint has done valuable work because they have adopted an integrated approach to assessing pesticide impacts across human, animal, and environmental health. So they have tried to follow a more holistic approach to this. And also they gathered evidence on real life exposure, assessed mixture toxicity, and quantified cumulative risks to enable that. So this is an important avenue that has been explored, because one of the challenges we face is that the current risk assessment frameworks are designed to operate in an assessment that is done substance by substance. And we know that the reality could be different because we have an exposure to multiple substances and sources in practice. And on the left side, you see that we tend to look at our piece of the puzzle in isolation. And we might not be interested to see how it interlink or interoperate with other pieces of the puzzles, for instance. So that has its limitations and some of its strengths. So on the right side, you see a more integrated and holistic framework where people collaborate jointly to frame the issue together and also splice the cake in such a way that it can be brought together and that all the pieces of the puzzle fit together. And it is important to have this holistic frame in mind, because by looking at your piece of the puzzle in isolation, you might not be able to see solutions that are straightforward. So the second important avenue explored by Sprint is that they try to provide tools and data for regulatory risk assessment science. So we have already had a quick overview of what has been developed, so I don't want to repeat that, but I mean, the pesticide monitoring on the real life conditions is something important. They have also modeled environmental fate of pesticides. They conducted a set of toxicological tests, including for non-target organisms. They assess mixture effects, cumulative risks. They develop new indicators and also provide some recommendations for policy and regulatory integration. And this is important because the reality is that typically there is a bit of a gap between academic research and regulatory risk assessment science. So both activities are scientific activities, but they are performed in different reals with different purposes, approaches, different uses of the data, and also different testing of the hypotheses. So from a regulatory perspective, so if we talk about risk assessment, typically the goal is to support regulatory decisions. So we evaluate specific risks. And the approach we follow is a risk hypothesis need-driven approach, where you rely on reliable tests that are standardized as much as possible. So there is a bit of a nuance. So not all academic research can feed regulatory risk assessment science. And activities like Sprint try to bridge that gap. And I think it's important that when you want to ensure regulatory relevance, it's important to make sure that you engage with risk assessors and regulators to understand their needs, and also tailor your research and innovation accordingly. And that will enable you to deliver fit for purpose and ready to use tools and data in the regulatory context. So that's an important achievement. And with Sprint, I think EFSA had the privilege to engage with Sprint. So we had an EFSA representative serving in the Sprint's advisory board. Sprint also contributed to our one conference in 2022, where it provided an important contribution. And we recently also had an internal meeting with our Sprint colleagues to exchange on the latest data that they had gathered over the 5 years project they run. So we are very grateful for that exchange. So it's important to have that engagement early as possible in the process, and also throughout the process, to make sure that we can build on each other's experience and frame things according to the respective needs. The project, I mean, it's not just delivering the data, but from an EFSA perspective, the next steps will be to explore ways to apply the findings that Sprint will report, and see whether we can apply those findings in future risk assessment. It might also guide future work on our level in terms of development needs and priorities. And then also, there is a need to enable the implementation and the regulatory uptake of some of the relevant data. So sometimes, I mean, data tools are being made available, but to have them fully implementable in a regulatory context might require further action. And there, EFSA can also play a role in achieving that. An example is, for instance, the interlink between prospective risk assessment, where you try to predict risks, and the actual retrospective risk assessment, where you monitor the actual impact of your combined effects. That interplay is something where more work should be done, because I think the reality might not always be fully captured by a prospective risk assessment. So it's important to see how these two environments can be better interconnected in the future. I will skip this one for time constraints, but I just wanted to finish with two important recommendations. The first one is not only for Sprint, but other research, academic research projects, is to realize that the closer your research touches on the regulatory arena, the more important it is to work closely with risk assessors and regulators to accomplish impactful work together. So make sure that that engagement takes place as early as possible in the process, so that we address each other's needs. And the other recommendation is that we should evolve from one-to-one engagement towards a more strategic partnership and a kind of platform-based collaboration. Because yes, EFSA Sprint is one-on-one engagement, but we have other important Horizon Europe projects running that are complementary and delivering equally relevant data. So it's really important that we all benefit from that to avoid duplicating work and complementing each other. So perhaps this is another important recommendation to take in mind, is that we need partnership and platforms to share the knowledge more broadly among all the different actors. And with that, I wanted to thank you for your attention. Thank you.
Thank you very much, Yann. And next, I'd like to invite Isabelle. Isabelle.
So, thank you. As it has been said, I'm a professor of occupational health at the University of Bordeaux, and I lead an INSERM research team that is focused on environmental risks. So I was also responsible for the case study in Bordeaux area with vineyards as a crop of interest. So the previous talks have already addressed the question of the importance of such researches, and I would like to provide you a quick overview of what is already known and what is currently admitted about the health effects of pesticides. So it will come as no surprise for you that it is a highly debated topic where the line between rumor and scientifically validated facts is often blurred. And nearly every day, headlines reflect the ongoing public and media attention it receives. Here are some examples from recent newspapers. Even in Belgium, as you can see, we have titles about this topic. So the effects of pesticides can be investigated through multiple complementary scientific approaches at different levels. Experimental sciences, such as toxicology, help us understand how pesticides act on molecules, cells, or organs. Medical data can also help as they offer insights into clinical outcomes, more in the situation of poisoning, acute poisoning cases. And at a broader level, epidemiology examines the impact of exposure on workers and the general population too. So these different scales of investigation each provide valuable information that are complementary and have their own specific strengths and limitations. So to summarize the current scientific knowledge on the health effects of pesticides, I chose to, because I had a short time, to present you the key findings from a group of experts in France who conducted a collective expert reports in 2013 and 2021. And these assessments you can find, they are available on the INSERM website. And there's also an English summary, so it's accessible for everybody. These reports aim to inform public health decisions through a comprehensive review and critical analysis of the scientific literature on the topic of health effects of pesticides. The multidisciplinary team included in this work were specialists in epidemiology, exposure sciences, and toxicology. The goal was to clarify the associations between occupational pesticide exposure and chronic diseases from existing literature. The analysis also considered data on health of children through early life exposure, particularly during fetal development and early childhood. And the work also tried to identify specific active ingredients or groups of pesticides that were potentially responsible for these outcomes. So after reviewing approximately 6,000 scientific articles, so we can say that we don't know anything about pesticides, and engaging in extensive expert discussions, the group assigned levels of presumption regarding the link between pesticide exposure and the development of certain diseases. For conditions where evidence suggested an association, 3 levels of presumption were defined: strong, moderate, or weak. These classifications were based on both the quality but also the number of studies supporting the link. So these are the diseases for which the link with pesticide exposure has been assessed by the group. The two major areas supported by substantial scientific evidence are neurological diseases and cancers, with particular attention to specific outcomes, as you can see in the circles that they are listed. I won't tell all of them, but you can read them. In addition, data have been reported to other conditions such as respiratory diseases, endometriosis, and thyroid disorders. All of these conditions were carefully examined in the INSERM collective expert reports. So due to time constraints, I will go straight to the results, but it's 1,000 pages each report. So in adults, the diseases for which the level of presumption of a link with pesticide exposure has been classified as strong is shown here in yellow, and it includes for cancers non-Hodgkin's lymphoma, multiple myeloma, and prostate cancer. Sorry. Oh. Sorry. I don't know, is it for a long time? Wrong? No? So here are the diseases in adults that were associated with strong presumption. And you can see for cancers, non-Hodgkin lymphoma, multiple myeloma, and prostate cancer. For neurological diseases, Parkinson's disease and cognitive disorders. And for respiratory disease, chronic obstructive pulmonary disease, COPD, and chronic bronchitis. You see that there are many outcomes in the intermediate level, which maybe in the future can evolve to a stronger level of presumption. In children, high level of presumptions were assigned to leukemia associated with maternal exposure, brain tumors in children, behavioral disorders for pyrethroid pesticides, and impairments in motor, cognitive, and sensory functions for occupational exposure, as well as congenital malformations. So here are some of the conclusions that were drawn from this collective expertise. Despite growing evidence, important knowledge gaps remain regarding the health effects of pesticides. Just consider that some quite important outcomes like pancreatic cancer or other digestive cancers were not investigated in the collective expertise due to a lack of data on the moment. And data on specific active substances were still critically lacking. Another point is that in Europe, exposure patterns, in France and in Europe even also, exposure patterns remain insufficiently characterized, as most epidemiological studies have been conducted in the United States. And you know that there are different agricultural practices, different pesticides use, different pesticide exposures, and then maybe also different diseases. Moreover, the health effects of combined pesticide exposure remain poorly understood on the moment. Sorry. And so there is a need to fill this gap too. And moreover, the last point is that the combined effects of pesticides remain also poorly understood, especially for the complex mixtures with distinct toxicology properties. So we also need retrospective identification of pesticide use in the past. For chronic diseases, it's really crucial. And we can say that through its multidisciplinary approach, the SPRINT project has aimed to bring new insights into this incomplete landscape of health effects. Thank you for your attention. Ça passe pas comme il faut.
Okay. Great. Thank you very much to our introductory speakers. Thank you. We will let you escape the stage. What we've done now is frame why the project is important and what is at stake. So I'd like to invite our next speakers to the stage, please, Violette and Lindsey. who are going to set out, Violette is going to give us an overview of the project, and Lindsey's going to set out the policy context. So, Violette.
Yeah, thanks for the kind words, and thanks for you all being here online and with us. I'm really happy and I'm really proud that we now did 5-year sprint, and I think we have something to tell, and there are a lot of questions open. So I hope there will be people who will follow up with our results, and Park is already on this, so I'm very happy about this. So, okay, we are in a very polarized world. If I go to farmers, no, sorry, this thing doesn't work very well, I think, with me. Let me just see. So, the question is, how can we feed the world? And there's a strong narrative. When the war in Ukraine started, suddenly there was a strong narrative in Europe. We will not be able to feed the world. We will not have enough food. This was a very, very strong narrative, which came after the farm to fork strategy was settled in the European Union to say we must reduce our pesticides. We are poisoning the world. So here we have these two polarizations. And Sprint tries to find a solution, an idea to give for further generations. The main questions are how we can find a balance between yield optimization and feed the increasing population, food safety, and the global health. Which are the needs and requirements for sustainable solutions? Maybe we know them all. There were thousands of projects going on as well on European level. Maybe the solutions are there, we just don't implement them. Is this possible with pesticide reduction? What is the actual health risk of pesticides based on real-world data? And yeah, the farm to fork strategy didn't get through approved by the European Parliament. So what is the future? I just give you a very short overview about the world's agricultural land actually used for food and feed production. As you can see here, the habitable land, 45% is used for agriculture and 38% for forest. How do we use this agricultural land? 32 million square kilometers are used for grassland. That means indirectly production of meat or dairy. 6 million are used for the production of feed and 8 for food. So is there a possibility to change from feed to food and feed the world? And I found something very interesting as well. The yields from organic farms are about 20% less. I don't know whether organic farming is the only alternative. I don't think so. There are a lot of agroecological approaches. But what is very interesting is to look at the diet of people actually. How do we feed the world? And why do we think we do not have enough food for 10 billion people who are expected to be there? I found this very interesting overview. How many calories do we produce per day? And that is more than 2,700 calories per day, per person, per world. And here already taking into consideration the losses by harvesting. So do people die in this world of hunger because there is no enough food? Or is it a distribution problem? The average need of an adult person is 2,500 calories. So even if we take 30% of food waste into consideration, we have enough food for the whole world. And if we take here as well the planetary health diet into consideration, which you can find this concept very well elaborated, there is enough food. So there is a possibility to reduce pesticide and to change the agricultural systems. And that is where Sprint comes in, and which was the open question of the European Commission when Sprint started. What we did not know, and we already saw here in the beginning of the first three speakers a little bit about this, the pesticide residues in terrestrial ecosystems, humans. We did not know how high are the residues in real worlds, always based on modeling. As Yann already said, there were no approval procedures in place to testing mixture effects. We need integrated reference values for all exposure routes, not only for food and drinking water. Linking fate models to large-scale monitoring data, including the transport of wind erosion. This is another story which was sold a long time. If pesticides applied on a field, they will only be transported from the field in the solute phase. So it will come to surface water in the solute phase, but nobody ever took in consideration in the regulation the strong transport by wind erosion. And we all can see our windows being dirty in springtime. This is an effect of wind erosion transported the fine particles of the soils from the fields to our windows into our houses. And linking fate models to large monitoring data, as I said, and then as well, and this we will present here in the following sessions, improved set of sensitive indicators for toxicological and ecotoxicological tests. So how can we simulate in these tests the real world and not just taking one species, which is a good laboratory species, to test whether a pesticide is safe? And here we come as well to the farmer's perspective. The farmers apply the pesticides because they are told they are safe. So the farmers don't do anything wrong. They follow the rules. So therefore, we need a transition to sustainable agriculture, and therefore, we need as well a lot of stakeholders to be involved as we do in Sprint. And here, when I come to the overall aim of the Sprint project, which you might all know, it's develop, test, and validate and disseminate a global health risk assessment, taking resilience, reproductivity, and manifestation of diseases into consideration, and showing pathways, and here we have our experts in the consortium who are working with these pathways towards sustainable agriculture in a multi-actor approach. The workflow. So what we did, we collected in 10 European countries and Argentina in a real-world setting with under organic farming system and conventional farming systems, ecosystem matrices and human matrices to see what is the actual state of pesticide in these matrices. And then we estimated the exposure to humans. We made ecological and human toxicity assessments, developed new laboratory tests, and as well advanced in exposure modeling and risk assessment. We engaged our stakeholders on national, regional, and international level. And ongoing is now still the development on the toolbox because thanks to Bela's activities, we get a prolongation for half a year for the sprint. So you will hear from us the next half year still. So I think you all have seen this in the first video where we took the samples. It was an extensive work we have done there. And then I just will go here for the first one result, and Abdallah will show more about this. What we found here, you can see here the number of residues. I think maybe you have all seen these already. These are omnipresent mixtures in all farming systems, in conventional farmings more than in organic farms. But what is here very, very visual is that all these pesticides accumulate in indoor dust. And here we have until a maximum of 120 different pesticides in farmers' houses, pesticide residues with unknown risk for the people living there. And hopefully we can come to risk assessment for this inhalation, dust ingestion in future, because this pathway, following the existing EFSA regulations and fate models, these could not be there because there is no transport with wind erosion, there's no transport by clothes, by shoes, by things which you buy. This transport is not considered, and this is the most important exposure because you're exposed daily by this. So, and as well, interesting thing here to show is, if you look at here the hazard classifications, we took them from the PBDB database. here for approved candidates for substitution and non-approved pesticides, and looking for them here for cancerogenity, endocrine disruption, and reproduction development effects. For the indoor dust samples, what you can see, red is very red is hazardous, yes, possible is a little bit lighter red. So what you can see here for cancerogenity, it is even for the approved ones, there are about 30% surely or possibly cancerogenic. For endocrine disruptors, we have a lot of unknown data because it was only recently included into the regulation. But for the reproduction development, we see that we have about 60% of these pesticides which are found in the indoor dust are classified as possibly or yes hazardous for reproduction development effects. So what is the consequence for people living there? What is the consequences? What is the concentrations? We don't have maximum residue levels for these compartments. So what can you tell a farmer whose child is playing on the ground? So we will see today the toolbox, the challenge, because you have hazardous data, and to know what is the real risk, you have to look for the exposure. So this is what will be taken, what will be shown today with our colleagues, Nelson and Daniele, to show how do they tackle this with new laboratory tests, and what we will do in the toolbox today be shown by Jakub. And this is what you can expect. Pesticide residues and impacts. Pesticide residues will be shown by Abdallah. In humans will be shown, I think, by Paul. Then the toolbox by Jakub. The regulatory context, recommendations from policies and implications, that's by Lindsey. The transition, cost-benefit, will be shown by Farshad and Claudia. Transition success stories. So there are stories which succeed. There are people who can do it. And there's a lot of people, I know, farmers who did it. And I personally am convinced it's a mindset change, because we tried everything in policies to make changes, and it is very, very difficult. But the mindset change, farmers can do it and can work in an agroecological way. So this will be shown by transition stories. Yeah, and we will have as well these policy recommendations. And last but not least, a very important thing in Sprint is the stakeholders train the network. We need them all. We need all groups, all sectors to work together and stop with the polarization, go together for a sustainable future for us all. Thank you.
All right, let's see.
This works by itself.
Did you present this?
No, it's too much. I just skip it.
Okay, so I go past this, yeah? Yeah. All right, can we hear me? Yeah, I think I can make this pretty brief. My name is Lindsey Hendricks-Franco, and I'm with our policy partner in the project, Ecologic Institute. And I just wanted to spend a few minutes here framing some of the policy considerations that we should keep in mind as we go through today's presentations, given that we're here in Brussels and we have a wide audience of stakeholders, many working in policy and many who may not be familiar with the entire context of EFSA's risk assessment process, et cetera. So for our 300 or so people in the audience, I hope this helps frame what we'll hear today and where you can focus your attention. So as we've mentioned several times today, we have a procedure for the European level for evaluating the safety of pesticides and plant protection products. Just want to briefly summarize how this works so that the presentations from today make a bit more sense. So the authorization of plant protection products and individual active substances, as we know, is governed by the regulation 1107/2009, and this is an overarching regulation that guides this process. As mentioned by Yann Devos from EFSA, our individual active substances are approved at the European level through a repertoire member state and evaluated by the EFSA, the Environmental Food Safety Agency. Later, plant protection products, and so this is the actual mixtures of active substances, are approved by individual member states and accepted in zones, common zones. Yeah. And then finally, there's a procedure for reauthorization. So how do we actually incorporate new data when it comes about over the course of these usually 10-year cycles of approval? So we'll talk about more about this, but a lot of what we'll hear about this morning is really related to this process. How do we assess the risk of pesticides before they're on the market? On the other hand, we have procedures for post-market surveillance. We talked about monitoring and linking real-world data to the effects of pesticides. And compared to this process here on the left, the pre-market authorization, this is actually contained under many different pieces of legislation, policies, and strategies. So we'll go through this. We also have strategies for reducing pesticides, such as the farm to fork strategy or the biodiversity strategy, which set the intention, but not the legal requirement to reduce pesticides, most harmful pesticides, by 50%. So what we have here on the left, of course, the way that we authorize pesticides before they're on the market is a strong regulation. It's very kind of tight loop of how this works. But when it comes to the real world data monitoring and our efforts to target risk reduction, it's actually contained across many policy areas. And as I mentioned before, taking that real world data and feeding it back into the risk assessment process is not as clearly articulated in the law. And so our colleague from EFSA already mentioned this. Overall, in the European framework and risk assessment, we're looking for better ways to link real-world results to risk assessment. So today, you're going to hear a lot about, hear about terms of exposure and hazard toxicology. So just to remind, when pesticides are assessed, we have data regulations that lay out the requirements for this kind of testing. And so when we talk about that today, this is what we're referring to. As Violette mentioned, the risk is made up of hazard times exposure. So we'll be hearing about toxicology, so ecotoxicology, and then human toxicology studies, as well as exposure. So how do, in the environmental risk assessment, how do molecules move through the environment and with potential exposure to life in the environment. And then in human health, exposure through diet and non-dietary exposure are regulated in slightly different ways. This is a dense slide, but just to say, as mentioned before, Yann Devos from EFSA used the word fragmented for EU policy around some aspects of risk assessment. And here I'm talking about monitoring. So in Sprint, we put the whole story together and we monitored in one big campaign all of these different matrices, so soil, air, water. But in reality, when the EU policy, these are often regulated in different policies and laws. So for food, we have strict limits called maximum residue levels, and there's also strict limits in drinking water, and of course, obligatory monitoring campaigns that check for this. On the other hand, we have no standards that are set for air, soil, surface water, and the indoor dust we heard about. Even within the soil monitoring law, there's, well, I'll just jump down here, we have no legal thresholds for action yet. However, the soil monitoring law still is a big step forward, and there will be monitoring of pesticides on a watch list, which is still being developed by the EU and also member states. So in the interest of time, I'm going to leave it there, but I'll just put this slide up and remind that for each of these areas I've discussed, we'll be hearing results today that can support this. So Violette mentioned this as well, but for pre-market risk assessment, we'll hear about new methodology for bringing realism and accounting for uncertainty, considerations for monitoring in the environment and in human samples, how can we use monitoring data to prioritize our measures and the pesticides that we reduce? And then how do we scale up and transition using instruments like the CAP? So with there, I'll leave it. I hope I've made up a little bit of time. And we'll move on to our scientists.
Thank you very much,
Yeah.
Lindsey. Thank you very much. We'll let Lindsey and Violette escape the stage. That's great. That gives us an overview of the ambition of Sprint and what's at stake. Just to remind you that particularly in the magazine that will be in the pack you'll find all of the references to the papers that we've already published and much more detail about the findings of Sprint. So now I'd like to invite Abdallah and Nelson and Paula to the stage, please. We're going to take a deeper dive into the science. You've heard these speakers already kind of trailed. So this is where we go next. If we have a little bit of time at the end of this session, we'll have some time for some questions and answers from the floor and possibly from online. We'll see how the time goes. So I'd like to invite Abdallah to start, please.
Good morning. Thank you, Matt, for the presentation. My name is Abdallah Alaoui. I am working at the University of Bern and leading work package 2 entitled Pesticide Distribution and Human Health. I am supported with, of course, many people and all case study site leaders and work package leaders, and especially Vivi Schlunsen. She is not here, but she was also co-leading, or she is co-leading work package 2 and dealing with the human aspect. The objectives of our work package 2 is the harmonization of monitoring of pesticide distribution in the ecosystem, plant, animal, and human, called here EPA, and the related health status. There were or are many open issues that we already learned from the literature. For example, the widespread and the excessive use of pesticides in modern agricultural practices has caused pesticide contamination of the environment, animal, and human, with confirmed serious health consequences. And this need some to try to link exposure to EPA health. This is what we try to do within the framework of Sprint project. I will finish with the general conclusions and some possible ways forward. Work package 2 was dealing with collection, storage, processing, and analysis of data collected at the case study sites, and the determination of the ecotoxicological risk for pesticides detected in soil and water bodies and other matrices and compartments, and the associations between pesticide concentration of different matrices as between source and the endpoints. And what I will show you, and we focus on it to rank the top 20 most frequently detected substances of potentially high health concern based on frequency and median concentration. We had, in general, 3 compartments, human, environment, and animals. And for human, we have 742 individuals, including 2,903 samples. And for environment, we considered 837 samples, and for animal, 816 samples, of course, including different matrices. Also, I will show you briefly some tables only as information. But here, for example, if we consider all compartments, meaning human, animal, and environment, we can see these top 20 substances. And we can see that we have 9 substances, not approved substances, with 9 insecticides containing or including 4 metabolites, 3 herbicides, and 7 fungicides with 1 metabolite. Here we can see also that we have within these 20 top substances, we have 9 pesticides with dual use, not approved in black, and we have 5 pesticides also with dual use that are approved. Okay, and then I have here, I marked the 6 substances that we found in all compartments. These in each compartment of, we consider like human, animal, and environment, they are everywhere. Okay, within the framework of our work and our project in general, we established, because we had many substances that we ranked according to their detection frequency, and we had to include also the importance in terms of median concentration. And for this reason, we established a ranking score to rank the substances, take into account of both occurrence frequency and or detection frequency and median concentration. This is only to rank our substances, and and my colleague Vera established a more comprehensive also prioritization indicators, including also directly the hazard aspect or issue, which is similar to the European Commission Harmonized Risk Indicator 1, and for these used or useful for different applications, such as to set monitoring priorities, support decision-making concerning pesticide use, approval, and transition, and also to assess pesticide pressure on ecosystem and human to define also benchmark values. We applied those indicators or in our assessment that I will show some results concerning those top 20 substances and their hazard. Yeah, here is an example. As you can see, we have the 3 compartments, environment, animal, and human, with different matrices that we considered within each compartment. And you can see here, some substances are found or detected in all matrices for environment, such as DDE-PP, chlorpyrifos methyl, boscalid, and chlorpyrifos that were detected in also both farming system, conventional and organic, and also followed by others that like glyphosate that is not detected in crop in organic farming system, and also the others in orange here, many others. Okay, here we can see, or this figure shows that in indoor dust, we found all substances we considered in this list. And very interesting. Also, specifically, or if we show these slides, also conducted by, or in the paper of Navarro et al. 2024, we can see the difference between also the homes of organic and conventional farming system with some detection frequency of different number of substances we have between, for example, less one is 25 to 30 and till 101 to 125 substances. In general, what we can mention here is that the mixture of pesticide were found in all dust samples, as I mentioned before, and the concentrations varied in a wide range, with glyphosate and its degradation product, AMPA, permethrin, cypermethrin, and piperonyl butoxide found in highest concentration. The insecticides showed significantly higher levels than herbicides and fungicides. Organic farms showed a significant lower number of residues, total and individual concentration than those related to conventional farms. I will show one or two other slides to illustrate or to highlight the fact that we found less substances in organic farming system compared to conventional, if we consider all compartment and matrices considered. Yes, here, based on the prioritization indicator we established in this study, we matched their potential effect on the environment, considering toxicity class, and the health of animal and human, considering level of evidence, also based on this database called Pesticide Properties Database that we mentioned in our respective papers. Also here some outcomes regarding, for example, the environment and animal and human compartments. We can see our data on the left side, this ranking score we established with our indicator, and also the matrices where they are found. For example, on the left side, we have 1, 2, 3, 4, 5, meaning earthworm, indoor dust, air, plant, and soil. And for example, for glyphosate, it was ranked on the top and found or detected in all matrices. And on the right side, this is what we have taken from the database PPDB. These are showing the hazard, corresponding hazard. I would like to mention that there are indicative information. And also similarly, we have the animal compartments, and we rank also in same way those top 20 substances, and we found as usual glyphosate, AMPA, DDEPP, and other most detected substances in both conventional and organic farming system. And for human, we have yeah, for human, also here we showed those top 20 substances ranked according to the score. And we can see, for example, the top one is DDEPP, and we see the stakeholder groups marked with C, referring to consumer, F is the farmers, and N are neighbors. And if the red text mentioned that we found the substances in the plasma of human. And also we have corresponding matrices, like, for example, one referring to feces, to urine, etc. And we have this one we have on left side conventional and on the right side organic. Also here, what we can, in summary, we see that among the top 20 substances, DDEPP has the highest ranking score. 12 of the top 20 substances are present in conventional farmers' blood plasma. And among the 20 substances, 4 are hazardous with regard to, for example, cancer, as the DDEPP, pepperonyl butoxide, and others. And 10 are classed as probably carcinogen, as the glyphosate and tebuconazole. Also regarding soil, we have also detection frequency of different crops, and those crops are related to each case study site or country. And we have, for example, here vegetable in Spain, wine, grape in Portugal and in France, etc. And we can see that here soil in general are very contaminated in many cases. These are for several substances or with different substances. And we can see in general that, for example, Portuguese soil, wine grapes had the highest number of substances, 12, with average concentration varying between 1 and 162 microgram per kilogram, followed by France and Spanish soil. And here I'm showing you the detection frequency of the 20 substances in crops. And we can see that also we have 6 fungicides in vegetable of Spain, and 11 fungicides in wine grapes of Portugal and France, and 6 insecticides also. And we have 5 fungicides in vegetable in Italy, and 5 fungicides in potatoes in Netherlands. And in general, we have 5 insecticides. We have 8 insecticides and 1 herbicides and 11 fungicides. Yeah, here we try to show the average concentrations in soil and crops to see if there is some correlation, not statistically, but only to see if, for example, we have an indirect relationship between them. And we can see that, for example, the blue cells shows that we have always higher concentration in soil than in crop. And orange showed that we have a higher concentration of the crop than in soil, etc. And we have some, maybe according also to the literature, we have some, we expect that there are some, for example, uptake by the crop, of course, in addition to the application of the pesticide by the farmer, but also maybe taken by the from soil. And this was also the case in many papers, especially maize, etc. And yeah, only some idea about this relationship. And here we have the pesticide residues in soil by country. And this is also published by my colleagues in different papers that you will find on website. Here in different matrices of the environment, we can see here, for example, as one of sorry. We can see that we have always more total concentration is always higher in conventional organic farming system than in conventional, for example, in soil, crop, air, indoor dust, and for water and sediment, we didn't manage to link them to the farming system since it needs some connectivity assessments. Yeah, here I have some results that I would like also to share with you regarding the environment, risk and environment based on the risk coefficient. And my colleague Nelson will go into detail with those investigations. And we classified based on those risk coefficient, we classified the risk in 4 classes. The highest one, for example, if this risk coefficient is higher than 1, it's meaning that the measured concentration higher than the PNEC value. Here we established the risk for in 4 compartments: soil, crop, water, and sediment. And for example, here, for example, here for the soil from conventional farms, we have 5 active substances: chlorpyrifos, glyphosate, buscalid, difenoconazole, lambda, cyhalothrin, and 1 metabolite. AMPA were considered high risk, for example, in soil, but also we have other, for example, here for crop, we have the high risk in tree in one case for 1 substance, meaning that's higher than 50% detection frequency. Okay. I have to conclude according to my colleague Jane. Also, we have here also summarized with 1 table showing the most the top substances having higher risk when considering the sum of moderate and high risk. And we, based on our data, we have published many papers also dealing with this aspect. And in summary, we have shown that we have shown that humans are mainly exposed to hazardous substances from the environment and to dual-use substances, evidenced by the presence of a set of common pesticide residue across all matrices, suggesting exposure to mixture of multiple pesticides. It will be judicious to consider biocide and banned substances which constitute a baseline of contamination found in different human matrices. And our study shows that soil are highly polluted and sediment can act, although it's not shown here, but sediment can act as a secondary emission source for surface water. Is there, but it's not applied on field, for example. And here we have some, I summarize some research gap that we faced also in our project, this mixture aspect or issue, which substances we have to consider, how many, of course, because we found many in each compartment or matrices. And also we faced the problem of reference concentration and the limit values that we have to take into account for a long-term period. And exposure, also we have to consider chronic internal exposure, not no. Also here, I have some possible ways forward, maybe is better to show here. We have ranked different substances. The top detected one with higher median concentration, but they are not all entering the body of humans. And we have the problem of mixture, which one we have to consider in this mixture. And reference values or limit values, concentration, and how to assess this chronic internal exposure. Some studies already showed that when considering the adipose tissue, we can look at the substances existing or detected with high concentration, like, for example, here is the case of DDEPP that we ranked among the top 20 in our study in SPRINT project. And to overcome those problems, we can assess the concentration, as I told you, in those tissues. And second, we have to carry out some biomonitoring and with some detailed survey to consider long time period. Thank you very much. Sorry for that.
Let's hand it. Lovely. Thank you, Abdullah. We're going to hand over to Nelson. Nelson, please.
Okay, hello, good morning. My name is Nelson. I'm from the University of Aveiro, and it's a pleasure to be here to share the results with my colleague, Paula, the results of the ecotoxicological assessment that was done in SPRINT. I will present the results of the aquatic ecotoxicological assessment, and then Paula will show you the results of the terrestrial assessment. Oh, sorry. So our main goal was to assess the effects of pesticide mixtures on aquatic and terrestrial ecosystems using mixtures that we found on soil and water. What was our strategy for testing? So, as Abdallah said, we measure pesticides on water and soil in 11 case studies, and based on the concentrations we found in soil and water, we define mixtures, a mixture for every case study that was the combination of 5 pesticides. How did we select the top 5 pesticides that we consider the most relevant? For the aquatic organisms, the selection was based for each pesticide that we found. We look at the risk quotient, that is the ratio between the PEC, the predicted environmental concentration, and the PNEC. So we extract both values from EFSA reports, and we multiply the risk quotient by the frequency of occurrence. So the top pesticides with the highest scores were chosen for further testing. In case this approach was already published in Stotten, so in case you can see with more detail, you can check this publication. For the terrestrial ecosystem, we employed a similar approach, but with some adaptations, namely for bees and beneficial insects. In this case, the risk quotient was calculated by the application rate divided by the LD50, and also this procedure is already published. Okay. So this approach resulted in 11 mixtures, 1 mixture per case study, for the aquatic and also for the different soil organisms that we tested. In terms of concentrations, of course, we include a control, means no pesticides, and this is what is the novelty beside mixtures. The novelty of SPRINT, we tested the measured environmental concentration, the MEC, and also the PEC, the predicted environmental concentration. And then, as a worst case, we also tested 3-time PEC and 5-time PEC. In this slide, you can see an overview of all the ecotoxicological assessment that we performed. So this includes different species, terrestrial species from different trophic levels, also different species concerning the aquatic ecosystems. And we also tested native species and also beneficial insects. So this provides new ecotoxicological information on the 11 realistic mixtures. And apart from the monospecific assays, monospecific means that we tested species individually, we also create a simple microcosms, a multi-species assays, where we can look for the contamination transference along the trophic web. For time constraints, today we will only show you the results of the monospecific assays. And focus now on the aquatic systems. So we tested different species, 2 producers, a microalgae and a macrophyta, 2 invertebrates, daphnids and a benthic invertebrate, the chironomes, and also fish. We used a zebrafish. Okay, and starting with the microalgae, we used the Rhaphidocelis subcapitata. We'll look at grow inhibition after 96 hours. And if we look at the plot, so in the x-axis we have the concentrations, the MEC, PEC, 3-PEC, and 5-PEC. And in the y-axis we have all the 11 mixtures concerning each country. So most of pesticide mixtures induced grow inhibition in this species. And we can observe that in PEC, 3-PEC, and 5-PEC, induced inhibitions higher than 30% for most of the case studies. Moving to the aquatic plant, to the macrophyta, we also look at the grow inhibition in this species, but in a longer period, after 7 days. We always followed standard guidelines, okay? And again, 10 out of the 11 mixtures induced grow inhibition. In this case, the PEC, 3-PEC, and 5-PEC induced inhibitions higher than 50%. And also important to highlight that even the MEC, the measured environmental concentration, for some case studies, Argentina, Czech Republic, and Switzerland, induced inhibitions higher than 10%. Okay, looking now at the Daphnia magna, we look at the mortality, immobilization after 48 hours. 8 pesticide mixtures induced lethal effects in this species. Again, PEC, 3-PEC, and 5-PEC induced inhibitions higher than 50%. And also important to highlight that in 3-PEC and 5-PEC, for some mixtures, the mortality was total. Beside the standard species, the Daphnia magna, we also used a native species that we brought from the field. We established a culture. So this allows us to compare both the standard and the native. And we found that
That was quite an effect.
Total mortality, yeah. Okay. So what we found, so 6 mixtures induced lethal effects. In the case of Spain and France, the PEC and 3-PEC and 5-PEC induced 100% of mortality. And of course, higher effects in the highest concentrations. So we found a similar effect between the standard and native, but more pronounced in the native when we exposed to the highest concentrations. Looking now at the benthic invertebrates, all mixtures induced lethal effects. The PEC induced mortality higher than 50%, and Again, important to look at the MEC, the realistic concentration that induced, in some case studies, a mortality higher than 20%. In the case of Portugal and Argentina, higher than 40. Okay, and finally, the fish, we used zebrafish. So compared with the other species, was the most tolerant. The maximum mortality that we observed was 25% in the 5-pack, and the French mixture was the most toxic, resulted in 21% of mortality. In this species, besides the survival, we also look at the neurotoxic marker. We used cholinesterase activity, and for most of the mixtures, we found a significant decrease. And we also look at the behavior, the swimming pattern, and we found a tendency of the larvae to spend more time in the outer zone, and this is correlated with the decrease in the cholinesterase activity. So to conclude, some key findings: all tested aquatic species were impaired by pesticide mixtures. In terms of sensitivity, we found Chironomus the most sensitive, followed by Daphnids, Macrophytes, microalgae, and zebrafish the most tolerant. We found expressive effects when we exposed the species to the predicted environmental concentration, and for some of them also for the measured environmental concentration. In some cases, when we compare the mixture toxicity with the individual NOAC or EC50 values, we found that the mixture was more toxic. And of course, the effects that we observed were highly dependent on the specific mixture and its composition. In case we have a mixture with more herbicides, of course, we observe more effects on the plants and the algae. So our findings underscore the importance of assessing the mixture effects. As we know, real world, we have a complex mixture, so species are exposed to multiple pesticides rather than an individual substances. Thank you so much. I will give the floor to my colleagues.
So good morning. So I will present now the terrestrial results we have. So we test for the 11 mixtures, different organisms, and today I will focus only in the soil invertebrates, which are springtails and earthworms, and also on the soil microbiota. So for the springtails, I showed same graphs as Nelson showed. The only difference is that for the terrestrial, we didn't test the 3-pack, only pack and 5-pack. But you can see the different mixtures and the concentrations. And in this case, we didn't observe an effects in the measured environmental exposure, the MEC. However, we observed effects on the predictive environmental concentration, the PEC. And in this case, when we check the concentration of these pesticides in the mixtures, they were close to or below the safe levels, that in this case are the no observed effect concentrations, the NOx, for reproduction in springtails. So what shows us is that based on these levels, we expect to see no effect. But as you can see in the graph, we observed higher than 87% of the reduction of the reproduction in these animals. So it was much higher than what we expected. Now are the results for the standard earthworm species, Eisenia foetida. Also a reproduction test was conducted. And in this case, we already observed effects at the measured exposure concentration. And also in 3 mixtures, we observed the same thing, that based on the concentration of the pesticides in those mixtures and the safe levels, again, is the NOAC for forms now that we used, the observed toxicity was much higher, and that occurred for the predicted environmental concentration pack for the Czech Republic mixture and for the 5-pack for Croatia and Argentina. And now these are the results for the native species Lumbricus rubellus, also a reproduction test. And in this case, also effects were occurred in the measured environmental concentration. And in several mixtures, we observed effects also in the predicted environmental concentration pack and 5-pack. However, in this case, because this species is a non-standard species, there's not much toxicity data on the single effects of these pesticides. So we don't know what are these NOx or safe levels. So it's very difficult to know if the toxicity would be what we expect or higher or lower. So we observed significant effects in different mixtures for all these 3 species. But when we gather them all together, it means that the 11 mixtures cause some effects at some of the concentrations we tested. So that shows the importance of using different species with different traits. Another thing is that we observed different toxicity between the 2 or farm species, because only the mixtures of the Czech Republic was toxic for both of them, while the other mixtures were different. And now I'll show the results for the soil microbes. So we followed 2 methodologies. The first one was based on the OECD guidelines. So we measured carbon and nitrogen mineralization transformations after 28 days. And according to the risk assessment, if the pesticides show lower than 25% of deviation from the control treatments up to 100 days of exposure, it means that they are safe. So based on that, we only continued the test and measured 56 and 84 days in those treatments where we also observed higher than 25% of the effects. And then a second methodology we used was we called novel soil indicators. And these are several endpoints that are related to the microbial function and structure in soil. And for this methodology, we measured soil in both 28 and 56 days. So for these OECD tests, we observed some effects in 5 mixtures, so we continued the test. However, after 56 or 84 days, all the mixtures the effects were not observed anymore. So that would mean, according to the risk assessment approach, these mixtures are safe. For the novel soil indicators, all mixtures affect one of the endpoints we tested. And in some cases, these effects were observed only after 56 days. So we would have this kind of, that at 28 days, no effects were observed, and after 56 days only. So in terms of the risk assessment, it means that these effects would be missed because we would measure 28 days and say, okay, no effects, and let's stop the test here. And we wouldn't see all these other effects. And if you want to know more about these results on the soil indicators, there are a few posters that Ellen brought here today, so you can check during lunchtime. So to conclude, the effects were observed at the lowest concentration we test, and I want to highlight here, these were the measured environmental concentrations. And not only for earthworms that I showed and the soil microbes, but also for bees, terrestrial plants, and predatory mites. In few cases, we observed that the toxicity was higher than what we expected. So it suggests to us that there was a synergistic effect caused by the mixture presence that we wouldn't see if these pesticides were exposed alone. And regarding to the new sprint indicators, which are non-standard tests, I want to highlight again this difference in sensitivity between native and standard species. So we can conclude that not always the standard species will predict the toxicity of the native ones. And again, the prolongation of exposure period might be necessary in the case that of these late effects that were observed on the soil microbes. And thank you.
Thank you very much.
Thank you.
Lovely, thank you. We have a few minutes for some questions and answers. I know that's already started online, so anybody in the room who would like to pose a question, and you could suggest who that question would be for. Jane and Vera are grabbing microphones, so you don't need to shout. So wave a hand or indicate if you have a question at this point. Okay, I'm looking, Jane, and okay, I think no questions at oh, please, sir.
Yeah, congratulations. My name is Jacob van Klaveren from RIVM in the Netherlands. Congratulations with the good research, and you show how mixtures matters. That mixtures has a big effect. But did you also test the single chemicals one by one so that you know what is causing the mixture effect? One pesticide, the two pesticides, or are there good pesticides and bad pesticides in the mixtures? Or was it only the mixture experiment?
So we didn't test the single pesticides, only in the mixtures of the 5 pesticides. So that's the downside, but would be very difficult to test all single pesticides due to the high number of species we had and also the high number of pesticides. So we have to choose.
Yeah, of course, there's a limitation of what you can do, but that was just my question.
Yeah, thank you.
I just want to add something concerning your question. We had some side experiments where we selected less numbers of pesticides. And for this, to understand the mechanisms, we of course measured the single effects as well as the mixture effects. And we very often have synergistic effects on that. But for some mixture, it's really that one toxic pesticides dominate the overall. It's not in all cases that it's a synergy. But I refer to the posters. We could discuss this at the poster.
And I would like only to add that you have these EFSA data on PNEX and non-effect level concentration and so on. So they were taken to be compared for the standard species. So these ones who were safe, thought to be safe, and we could see, especially for the earthworms, and as well, I think you did it, comparing, normally you have 5 pesticides and you look at the PNEX, there would not be at any effect, but we saw it. So what we did not have, we did not make the test for native species, for the single pesticides, but the data are available for standard species from EFSA.
Yes, I'm Margreet van den Burg and leading the gender committee. And because we didn't get very overt data results on difference in gender, it's not mentioned now, but I would like to stress that we continue doing that research because we did see in the farmers that male farmers were exposed, had more residues of pesticides in their bodies. But we're not sure what the women that were tested, whether they were actually doing farming or not. So I just would like to highlight also for the overview that especially humans are really different in bodies, and pesticides, especially in the long term, can have different effects. So although it's not said now, I would really recommend, and you can see in the poster we made, that especially for the longer term and for future research, we should keep on taking the difference between male and female humans, but also animals, and especially farm animals. We mostly have female animals like the cow, the chicken, the pigs. They have female bodies also. So there's lots more to do on that. And I wanted to add that.
Yeah, thank you, Margaret. This aspect is also assessed, or we dealt with this with the help and support of Anne and Vivi, and the paper is ready to be submitted. We consider this aspect deeply. Yeah, thank you.
Lovely. Thank you, Abdullah. And we'll look forward to that paper. Paula, who's doing the online, has got a few questions.
I have a question from Leo, and he is asking to Nelson and Paula. In the pesticide mixture experiments, did you use the active ingredient only or the formula as used in farming? Is there evidence that additives can make a mixture more toxic? I have heard this is true for Roundup and bees.
Yeah, we just tested the active ingredients, but from my previous experience with testing pesticides, commercial are more toxic than just the active ingredients. What they call inert ingredients are also toxic and make the commercial more toxic than just the active.
We as well made an experiment which is not yet published, and we are still working on this, where we applied or simulated the application of the farmers. They're using the real pesticides and testing the effects on earthworms. So that was done in Wageningen, but it's not yet finished.
Lovely. Thank you very much. Now, as a little change, just before we break for refreshments, Lindsey is just going to come and do a short presentation that will help us after we've had refreshments. So, Lindsey, please.
Yeah, just to come back around and wrap up some of these excellent research results into how this applies to the policy framework we discussed earlier. Yeah, as a reminder, we have considerations for pre-market testing of pesticide active substances and plant protection products, and also implications for monitoring and risk reduction once they're on the market. So we've focused on toxicology of these substances and how they move through the environment. So based on this, I just want to put up some of our recommendations, and you can read more about this in our policy deliverable and briefs that will come out. But yeah, so just briefly, mixtures required for pre-market testing should be better reflect the realistic use of PPPs under consideration. So that includes how are they recommended or required to be mixed in tanks? What are the typical application sequences for the other pesticides? And then also this background of pesticides in the soil. This is not necessarily easy to achieve, and it will require cooperation between regulators and academic researchers, but it's important to address in future versions of our regulations. We've heard that the single species tests can be expanded to add realism to the assessment, including more sensitive endpoints, so actual different types of tests that we conduct in the pre-market risk evaluation, risk assessment. Yeah, so that's something to consider. And then it wasn't mentioned here, but adding increasing safety margins for the allowable concentrations of pesticides in the environment. Given that we do have pesticides already in the environment and there may be some unknown effects, we can increase the safety margins for allowable concentrations. Yeah, we also can improve the way that we regulate environmental fate. Where do pesticides end up in the environment? So again, allowable concentrations or the predicted environmental concentration that's considered acceptable. So PEC needs to account for the background of pesticides already in the environment, which we've seen are many. And we need to continue to improve the modeling for the connectivity between different parts of the environment. So how the application sites of pesticides and how this makes it into other environmental compartments like water. Yeah, and finally, indoor dust is not currently addressed, and degradation models for pesticides tend to focus on the outdoor environment where there's a lot of water and light. And we could probably increase the focus on indoor degradation of pesticides as well, where they tend to accumulate. Yeah, finally, in our monitoring, as I mentioned earlier, we can see now that pesticides are appearing in many different environmental compartments, and our policies don't always set a clear binding legal threshold for how the concentration of pesticide residues and their mixtures that can appear in the environment. So in many existing policies like the Water Framework Directive, the Air Quality Directive, and the Soil Monitoring Law and its implementation in member states, there's an opportunity to add more binding standards with corrective action when these are exceeded. So also, as a reminder, we already set theoretical risk-based thresholds for pesticides in the pre-market testing. And so transferring this concept into the post-market laws is an important step that's missing. Let's see. Yeah, and we have the new soil monitoring law, which is a really important step forward for assessing soil health. And now that's basically approved, but we're translating this now to national law, national programs. So yeah, continue to strengthen the concept of pesticide residues in our new definition of soil health. And as we move into deciding which pesticides will be monitored in this law, it's important to consider the results of SPRINT for what pesticides will, because not all pesticides are going to be monitored in this law. There's going to be a watch list. So we can use our SPRINT-based prioritization index that you heard about today to identify the highest concern pesticides from monitoring data. We can make direct recommendations potentially to the chemicals to include on the watch list. And as these are translated into national plans, we would also recommend a stronger role for soil remediation and regional management changes when we exceed levels of pesticides that are considered safe. It's very ambitious, but we also think it's important. All right, I think it's time for refreshments. Yeah.
Right. Thank you very much. And I'd just like to thank Paula, Nelson, and Abdullah for their contributions, and just a little round of applause from them again. We'll take a 15-minute break now. Next up is human health, so you may want to consider what you have during your break. We'll see you in 15 minutes' time. Thank you. Lovely, thank you. We'll just let everybody get back to their seats and resume. It's always a nice thing actually to catch up with people over a cup of coffee, and it's one of the fun things about a day like this. But we do have a lunch hour coming up. So there'll be plenty of time for catching up. So can I invite, please, up to the stage, Paul, Daniele, and Eoin will be joining us online. So we're moving now to human health. So that's going to be, I think, of direct interest to all of us. Not that the zebrafish and other environmental factors were not of interest, but there's something very deeply personal when it's your body. So that's great. We're going to also have a little change to make sure that you can all hear. We'll have a change of microphones. So when people turn away from the microphones, you can continue to hear. So first of all, I'd like to invite Paul. Well, I'll let Paul introduce himself and the work he's presenting. Okay, thank you, Paul.
Thank you very much. Can you hear me well? How about online? Everything is okay with the sound? So I'm happy to have the opportunity to discuss. It's not on. Let me see. Maybe here. Yeah. Hello. This should be done. There it is. Okay. Is this better? Yes. Okay, thank you. So it's a great pleasure to introduce you to some human exposure data that we have collected by human biomonitoring. I was involved in that. My name is Paul Scheepers. I have a background in toxicology. I'm an associate professor in toxicology at the Environmental Science Department of Radboud University. And before I start to talk about this, I should acknowledge people being involved in this project. For the analysis, we work together with Wageningen Food Safety Research, Hans Mol and Jonathan Diaz. They are not here, but yeah, I'm presenting their work. And then also I should acknowledge Martien Graumans, who is here, and also Nina Wieland. And Nina did also the modeling, and she has a poster in the back, so maybe for later can look at the details. So why biomonitoring? I think it's a good way to collect some real-world data, and I think that's a unique opportunity to collect maybe not only a urine, but also blood and feces, because this gives us a good picture on what we see as occurrence or also as internal exposure. We'll talk more about that later. And then obviously we are going to compare. I will also do that during this presentation. Farmers, neighbors, and consumers, and within the farmer group, the conventional and organic systems, farm systems. Yeah, and I think it's of course challenging, and that was to relate our human biomonitoring findings to reference values. So that will be a big chunk of my presentation. You know, where are we regarding the exposure in the context of these frameworks of reference? So to remind you, when we talk about countries, actually we should be talking about crops and regions in these countries. So let's not compare by country, but more like by the type of farming and the crops involved. Also the growth season where we collect our data is actually from, I think, March until October or November in Italy. So it's, I think, a very large period of time. And then we have taken what I would like to call a snapshot. You know, we asked people on one day to provide us with the samples. And then, well, although, of course, the overall number is pretty good, you know, if you disaggregate in the groups that we are looking at, actually you will see that for each case study site, numbers are not so big. So let's be careful about jumping to conclusions when I show you some of the results. And overall, we were able to, you know, you have maybe heard the word 200 substances. That's possible for blood and feces, but there are some limitations of the technical limitations, and for urine, I think we just have a limitation of availability of the standards. So that's why the number in urine is much lower. And well, the way I would like to introduce the results are by this graph where you are looking at the number of substances that were detected above LOQ. And then you see for each case study, you see the distribution: farmer, conventional organic, neighbor, and consumer. And let's say the order is with intention. Let's say that maybe the conventional farmer you could think could be the highest exposed, and then maybe the organic farmer, and then the neighbor, and maybe the consumer could be the lowest exposed, you know, just as a theoretical assumption. And then look at the data, and then what you can see is, well, for blood, I think the median is around 2. So maybe you remember in the video, it says 90 substances detected in blood. That's also true overall for the whole data set. But let's say for the people who have participated, it's just good to remember that the median, so they have typically 2 substances per sample. And then you can see from this graph that maybe Argentina has on average a higher number of substances. And then I think I referred also already to a comparison within the population by subgroup. And then maybe let's take the example of the Netherlands, and there you see actually what I more or less expected to see. So farmers or conventional farmers have the highest numbers, and then maybe the biological farmers are closer to what we see in the neighbors, and then we see the consumers. But you can also see that this expectation is not becoming reality in most case study sites. So interesting for discussion. And then we're now looking at feces. So these data are really unique data, but because I'm not aware of any study looking at feces on this type of scale. And then last but not least, oh, sorry. I wanted to show, one also interesting. Yeah, sorry, that is the situation here in Italy, where in the fish sample, you see that the organic farmers are the highest. So that's, I discussed it this morning with Daniele. Let's say we should try to find out why, but that's to be discussed. Okay, how to interpret these data? And I'm also referring to the levels, because I've not been talking about the levels. I think it's pretty complicated to show you all these levels, but I think it's the most important question is, of course, do we see exceedance of current reference levels? And then we have two approaches. And the most simple approach is that the data that we have obtained from lab analyses, that you directly compare them to the so-called biological guidance values. They have been collected on this website. You can find it online. It's powered by the International Society of Exposure Science. And for pesticides, I think that you can find between 60 and 70 biological guidance values. And then it's fairly straightforward. Then I use this, what I call risk plot. What you see here on the X, you see exposure, just from left to right, increasing exposure. And on the Y, you see toxicity. Well, a representation of toxicity, also from below to the sky, let's say, increasing toxicity. And basically that means that, let's say, if you leave to the, go to the right or up, then you will go from green to yellow and maybe to red, you know. So that's why the colors are distributed like this. And then you see in the middle, I put the data in such a way that in the middle you see the reference value, in this case the BGV. And then I plotted the data by case study site, but not the median. So for this presentation, I thought maybe it's good to just plot the P95, and that means that all the data, or 95% of the data are below the point that I'm presenting here. Okay, and that's for, and then also, you see on the legend that maybe we should also take into account in how many samples we were able to detect the substance. And that's all, in this case, it's quite high numbers for chlorpyrifos. But for deltametrin, you already see very big changes, like from Switzerland, only 6% of the samples were positive, up to, I think it was, yeah, in Portugal, the highest, 93. So there you see also that Portugal has is a bit more to the right. So interesting for Portuguese situation to see to look at the case study site, you know, and the participants involved. So this is the kind of overview, and then a third example for 2,4-D. This is a herbicide where you also see a great variability, only 3% in France and Denmark, but also very high values, for example, in the Netherlands. So interesting, I think, for comparison. But all, let's say, below this dotted line. And then I come to the work of Nina, because she has done a lot of work. And I would like to present this as data that, regarding the presentation, are based on human data. So human data, let's say, from the collected materials, and also human data to do back calculations to values that we can compare with the ADI. So maybe to stress, not human data regarding the derivation of the ADI, because that's mostly done using animal data. And then maybe good to know that modeling is not just mathematics, it's a lot of based on assumptions, and then where the human volunteers come in, that is that they have been tested. You know, they were instructed to stay away from some food products for a couple of days, you know, to try to have a good low starting baseline level for a particular substance. So now I'm going to show very similar results, but first maybe to just explain, and I think this is also a graph shown on the poster, that in the modeling you want the model to describe the data that you collected from, in this case, the human volunteers. And then you can see that Nina was able to construct a model that nicely describes actually the experimental data. So it's a bit complicated because on the left you see the blood concentrations on a 10-log scale, and then the development over time, and then the urinary excretion is expressed as percentage of dose. But if you want to have the details, talk to Nina. And then again, this is also, and then we can compare to ADI, and ADI is of course a worldwide, let's say, agreed reference. And yeah, I think that, yeah, the interpretation is the same. And here for glyphosate, you see where we are. And then you see also for a second example is for tebuconazole. You see also where we are now regarding this substance. And this could be done for more substances, but of course, then you have to run these human volunteer studies, or at least have reliable modeling for the back calculation, the so-called reverse dosimetry. Okay, and then I think I would like to refer to a workshop that we had yesterday. Maybe you heard about that. Together with our colleagues from RIVM. Some of the people from Sprint are also active in PARC, and we are trying to use the data from the field campaign, from the case study sites in Europe, to analyze them in what is called the MCRA, the Mixture Risk Assessment method. I will not go into detail, but maybe it's interesting for you to follow up this work, because we are going to do some calculations to understand the risk of mixtures using common assessment groups. Well, I think it's time to sum up. I don't know how I'm doing time-wise. Yeah, okay. So maybe good to mention that overall we did find a lot of substances per matrix, but the numbers, let's say, in each sample are low. And I show the numbers here as a median with range. And then, yeah, regarding concentrations, of course, there's a very wide range. Let's say the data look like the data that we also see in other studies are scattered, and they are not normally distributed. So it takes a lot of effort to present the data in a good statistical responsible way. And we are dealing with a lot of non-detects, and that's, I don't know if you're going to talk about that, but that's a discussion on itself, you know, how to treat the non-detects in a analysis. And then I think that actually I was expecting to see much more differences between the subgroups that we found, but only in few cases. So interesting also, I think. And then maybe I think it's interesting to just look at the case of acetamiprid, where we see that the metabolite actually is very prominent in the kinetic pattern. And also Nina will probably be able to tell you more. So we should be looking at the metabolite. And I think also EFSA is aware of that. I noted that recently they decided to reduce the ADI by a factor 5. And also they are going to reduce the MRLs, the maximum residue levels in food commodities, by a factor, I don't know, we have to wait and see, but it will be done in August, I think. And that was in response to some concerns, also related to the data gaps that we have currently on the effect. And then, well, I showed you the risk plots. I think that we have to discuss what we think about this. You know, are we safe for these substances? Can we produce more of these plots maybe in the future? And talking about the future, I think that we have to be honest and say, yeah, we were doing a fantastic, I think, job in the Sprint project, you know, to collect all the data. And I think that Abdallah and Vivi were really well coordinating that effort. So we have comparable data across Europe. Thank you. And but of course the problem is that many people said, yeah, what? So you have collected your data on a Monday. What happened Tuesday and Wednesday? You know, in that environment. So of course that's true. It's a kind of snapshot situation. But that's of course a choice that we had to make. But now we have of course questions around all the limitations of this type of strategy. And I think for the future, it will be interesting to discuss feasibility of doing the time-resolved type of sample collection and data analysis. And I think that will be, interesting for discussion later. But first, and that will be my last slide, is to discuss the perspectives for biomonitoring. I think biomonitoring is a very good tool to collect data on multiple substances and internal exposure. But let's say from the numbers, you cannot see where they come from or how exposure was happening, you know, by inhalation, dermal exposure, or ingestion. That's not in the data. So we need human biomonitoring to be supported by good modeling. And I think that's also something that we have been working on. So that will probably be a good tandem. And then if we want to move on, and that's obviously also in the interest of the participants, because you can present, you know, whatever value, but in the end, the question will be, what does it mean for my health? And then you need the biological guidance values. I think it's a much easier approach to work with biological guidance values. I think we also can do comparison with ADI, but that takes more effort. So I would say, let's prioritize for which type of substance we need to do more, and also involve maybe human volunteer studies. And then, let's derive also biological guidance values for vulnerable subgroups like young children, like pregnant. Let's say I would like to also have values for women in childbearing age to make sure that these are also well protected. And then we need some maybe studies in workers. I would like to refer to the American or the agricultural health study that you also mentioned, Isabelle, where they have very good data on farmers because they are supposedly, well, the highest exposed, and also including their families. So maybe that's also maybe priorities. And we need then also the use of biomonitoring in future EPI studies. Last but not least, we're going to talk to IPChem to make our data available in this platform. I think we are just starting this, but I think that's also very important that in addition to the scientific papers, we also have availability of the data on IPChem. So I think that's it for, last but not least, I of course would like to thank all the study participants, you know, who have been willing to provide us with their samples. You know, it's very important that we work together with them, and of course the role of the coordination of all these field work activities, the case study site leaders. So thank you very much.
Okay, so we'll just invite Daniel, please.
This one, right? Hello, everyone. My name is Daniele Figueiredo. I'm an assistant professor in exposure assessment and planetary health at the Institute for Risk Assessment Sciences, Utrecht University in the Netherlands. Today, I'm going to talk about the exposure assessment done in sprints, an overview of the different things. We could not focus on everything on this presentation. So my focus will be on three things: dietary and non-dietary exposure modeling. It will be on wristbands, the measurements we did, and the duplicate portion analysis. So let's start with the dietary and non-dietary exposure modeling. As you see from this image, we are exposed via different routes. This is what we breathe in, inhalation, dermal contact, dust ingestion. We have the dietary intake, and also dermal contact just with the air around us, not just with surfaces. What we did was use models to do simulations at case study site level, meaning for each individual participant in sprint. And also, of course, from a risk assessment standpoint, you then have to move to population level. So then we also did it at population level by simulating using variability in age, weight, and many other parameters. Paul mentioned one very important thing, which is assumptions. Now, the models used was developed in a previous project, OBO, from the Netherlands, and then supported by another model called the DustX, developed by RIVM in collaboration with Finnish partners. And this is now in preparation in our package that will be available, I hope, soon. But I want to stress that there were some assumptions made. This is in discussion with experts. The first is we assume that concentrations in the outdoor environment were similar to indoors. This is based on previous measurements done in other projects, not done in Sprint because we didn't measure air indoors. Another important is the assumption that all pesticides present in dust are bioaccessible. Now, this is a worst case approach that we take here, because it can be that they're bound to particles, and when entering the body, they actually do not leave the particles. For dermal contact, we said that the frequency of contact, and here there were several assumptions made, such as the fraction absorbed to skin, they were lacking data. So available for certain pesticides, we had to actually use those pesticides to extrapolate to other pesticides. This was a huge gap. And finally, for dermal from airborne, basically what is around us, we assume there were no clothing barrier. And this is actually not a worst case. This is a realistic approach, because we also have pesticides in our clothes, so they can actually penetrate. So let's look at the first results. What you see here is dust ingestion, modeled hand-to-mouth patterns. Basically, we use the the EPA exposure factor handbook from the United States to derive also how much the population is ingesting of dust. And what you see here is an example for chlorpyrifos. On the left side, we have concentration in dust in nanograms per grams, and on the y-axis, exposure from dust ingestion. And this is represented also here in this distribution. And overall, for the pesticides we could have data to simulate, what we saw is that the max value corresponded to 1% of the acceptable daily intake. We also did this for inhalation. Overall inhalation had lower exposure ranges. It ranged from 10 to the minus 5 to 100 nanograms per kilogram body weight, considerably lower than dust ingestion exposure. And also for this route, we didn't see surpassing the ADI. And one important thing is that, of course, we are simulating all these exposures because in the end, what we can do is aggregated exposure by summing them all up. We managed to do that for several pesticides, and I'm just going to give an example here for acetamiprid. That's what you're seeing on the left side, where each of those distributions with exposure on the x-axis being milligram per kilogram body weight is an exposure type, an exposure route. So you have contact with surfaces, dietary, dust ingestion, inhalation, and particle to skin transfer. In this example, as I highlight there, you see dietary is completely contributing for most of the exposure. And when you do the summing of all distributions, which is on this right side, you see also the distribution looks exactly the same as the dietary route. In this case, contributed to 99% of the total exposure. Now we said, well, we have aggregated. Let's grab each of these pesticides and do cumulative. So what we did was just some examples for the nervous system, motor division, following EFSA report. We actually then added up all these pesticides. And what you see in the last distribution curve there is the mixture. So this is aggregated plus cumulative. And actually in this calculation, we saw that 1% of the population was at risk. Now I say this and you might be wondering, oh, 1%. But I should stress that we used a very worst case approach. In this case, we took the lowest NOAEL from the pesticide indicator as our target NOAEL. The approach normally is to also use these potency factors to adjust the potency of all the other pesticides. We did this worst, oh, apparently it's every time there's something big happening. It's a sensitive topic. So as I was saying, it's a realistic worst case scenario, high exposure from diet and environment. But if we were to use the approach on the top, the potency factor approach, adjusting each pesticide potency, then we would not see risk. We decided to use even more conservative. We're just taking the lowest NOAEL because we don't know if they're in a mixture, it will not be the lowest NOAEL that will be actually triggered. Oh, Now moving on to the wristbands. And it's loading very slowly. So it's just loading. I cannot do much about it. The suspense of the wristband measurements. Oh, and something happened. Shall I just fast forward? No, wait. Ah, perfect. Yes, thank you very much. So basically, the measurement principle is diffusion into the silicon medium and provides an indication of the non-dietary sources or routes. In this case, we did during the spring season for 2021 for 7 days continuously and subgroups, as mentioned before. And the results are, I wouldn't say striking, but reveal a lot. That, as mentioned before, we detected 173 pesticides out of the 193 analyzed. And I think what I want to highlight here is the occurrence that you see here in the bottom, that in 71% of the wristbands, we found above the limit of quantification 4 pesticides, permethrin, chlorpyrifos, piperonil butoxide, which is a synergist, and PP, which is a metabolite of DDT. And if we also take into account azoxystrobin, boscalid, and fipronil, 2 being authorized fungicides, which is azoxystrobin and boscalid, and fipronil being allowed as a biocide, all these 7 were detected in more than 30% of the wristbands across the European participants. If I put this into this complex picture, what you see here actually is on the panel A, the frequency in each of these subgroups, farmers, neighbors, and consumers. In the panel B, the number of occurrence by country in different colors, and the top 7. It's important again to highlight that from these top 7 predominant mixtures, permethrin and fipronil can be used as biocides, and chlorpyrifos and DDE-OPR legacy pesticides, which leaves boscalid and azoxystrobin, the only plant protection products still authorized as fungicides. So they give insight into prevalent environmental pesticide mixtures. We saw that organic farmers contained lower pesticide levels, although I didn't show here. Ownership of pets explained the pesticides that we saw that were used as biocides. We saw that banned pesticides were quite prominent, and that consumer wristbands never contained higher levels than all other groups. Finally, I go to the duplicate portion analysis. What we did here was collect all consumed food for 24 hours. And then we analyze for different pesticides and their metabolites. In total, 203 analyzed parent compounds. And in this case, not in all countries, but a subset of 7 countries. And a small population, so see it more as a pilot study of 43 participants. What I'm zooming in here is each row that you see here is a participant, and then on the top is all the pesticides we analyzed. I'm zooming in because if we look at the full picture, it becomes like this. And it's quite difficult to interpret this, but what I just want to highlight here is that we saw metalaxyl-M, which is still authorized, in all the DPA analysis, so in all food baskets, as well as the piperonil butoxide, which is the synergist. Although for metalaxyl-M, it did not lead to surpassing the ADI. Actually, none of the pesticides here in our individual calculations surpassed the ADI, but it's quite an interesting finding on the variability of the different pesticides across the different participants, and also on what we also found is that in 58% of the samples, and again, these people were not eating the same, they were eating different diets, we found these 5 pesticides above the limit of quantification. Metalaxyl-M, tebuconazole, and trifluxostrobin, all authorized at the moment. And ending slide is my main messages for today's meeting. The silicon wristbands were proven useful to identify environmental mixtures. For cumulative risk assessment, performed for the pesticide in food, it seems to be translatable also to aggregate exposure. So we can actually move and introduce more routes into aggregate and then cumulative exposure. Although, as I mentioned, there's some big gap on available data, especially for tox studies that are mainly for ingestion. For realistic worst case scenarios, our model did show that we can surpass the acceptable daily intake. However, we do not know if and how often it may occur. And finally, the DPA, the duplicate portion, did show that can provide a realistic data to calculate uptake to pesticides. Thank you, everyone.
Thank you very much. Hey, Daniele.
Okay, so thank you very much for the opportunity to present today. And of course, one of the aspects that I want to underline of the results that I'm presenting today is that they were obtained with the effort of many colleagues and institutions, starting from the Radboud University team, the Wageningen University, Wageningen Research, University of Antwerp, University of Cork, and Aarhus University. And in these 10 minutes, I will summarize 5 years of very intense work. So we generally put the knowledge at the end, the acknowledgements at the end, but I wanted to put it first because I really want to acknowledge the honor and the privilege to work with all this team and in general with all the Sprint team in this project. So what we did in the human toxicology work was to approach using a tiered approach that started with in silico, then in vitro and in vivo testing. What were potential knowledge gaps that emerged through Sprint? And the methods that we use were heavily based on the tiered approach that was proposed already by EFSA guidance in 2019 on how to assess multiple chemicals. So specifically, we used the component-based approach proposed in the guidance for human toxicology. And without digging in too much detail on the different tiers, we started with tier 1, where with a in silico assessment, we aim to prioritize from the more than 200 pesticides that you saw were addressed in Sprint, a top 10 that will be then assessed and addressed in the in vitro work. And now we did that thanks to mainly a weighted hazard quotient, the use of weighted hazard quotient, and the data that we retrieve from the Sprint CSS data and the EU pesticide database. So in tier 2, we address the top 10 components of concern using both what we called in our grant EFSA tests, which are tests that are more in line with standard toxicological tests, and what we call new Sprint indicators, which are new proposal, let's say, that we have in Sprint, either in terms of outcome or in terms of models that we are using in Sprint. And tier 3 was for animal testing. As you all know, we are aiming to reduce as much as possible the use of animal testing, and therefore we try to prioritize the most concerning compounds to be tested in animals based on the previous study. Again, also here, using what we call EFSA tests, so more or less standard 13-week study, here specifically prenatal study, that will allow to address a number of outcomes of interest in toxicology, but also new Sprint indicators, and you will hear a little bit more after me from my colleague Eoin, the details of that experiments which occurred in mice and aim to test behavior and microbiome changes and the interplay amongst them. And of course, also the contribution from University of Antwerp with kidney electron microscopy to enhance and had a better understanding of the potential toxicity of the pesticides that we tested. So an important aspect of toxicology is that, of course, we use in vitro or in vivo models And therefore, we try to predict what this means for humans. And two aspects are important. When we evaluate hazard, which means, whether something is or is not a carcinogen, is or is not a reproductive toxicant, we don't discuss much about the dose. So that can be informed by different stream of evidence. For example, in vitro and in vivo, and in silico as well. It becomes more complicated when we approach dosing, and therefore we generally extrapolate for animal studies risk estimates, and we approach that using factors that consider that humans are not laboratory animals, and this is generally adding an extra safety factor of 10, and the fact that persons, human beings, just like animals, are not the same. Some of them are more sensitive, some of them are less, and therefore we apply an extra safety factor of 10 as well. What generally this means is that if we find something at a level 100, generally the safety factor in humans is at least or even less than 1. So while I hear from Jane that I should speed up, the micronuclei results first, which are the genotoxicity results that we had, did show in all pesticides, but one that was just too cytotoxic, at least a positive signal of genotoxicity. These are results for glyphosate, tebuconazole, acetamiprid, cyprolambda, deltametrine, and cypermethrin, PBO, fluorpiran. And as you can see, for imazalil, it was just too cytotoxic to show genotoxicity. Micronuclei tests are a standard way to approach genotoxicity, and similar findings were also present in the mixture and both of the top 3 and the top 8 of concern. What this suggested was that indeed we did found additive but not synergistic effects with our genotoxicity assays. You'll see that something similar will also be shown by the other experiments. Cytotoxicity, again, excuse me for the pack slide, but the message is very similar to the one in genotoxicity. We observed a cytotoxic effect, particularly at the highest doses tested and consistently among the top 10 that were prioritized. But again, both for the top 3 and the top 8 that were tested together, we didn't see synergistic effects, but rather additive effects. So moving forward to some of the new sprint indicators results that we had alteration in terms of gene expression in kinase cell lines that were observed and used as new sprint indicators. We had alteration observed also in organoids, particularly piglet organoids that were observed. And also here we didn't see any additive effects. And actually we also saw one of the limitations that you will see at the end of our discussion, that it's very complicated when in human toxicology you add more and more and more and more pesticides to the mixture to disentangle the effect of one or the other and to try actually to provide meaningful results that can be used for risk assessment. So for the in vivo experiment, you'll hear more about the UCC experiment later by Eoin. I will summarize here what we did observe in the Ramazzini Institute rat experiment. The alteration of liver enzyme that was observed in all the top 3 of concern compounds tested, which were tebuconazole, acetamiprid, and glyphosate, respectively a fungicide, an herbicide, and an insecticide. Also here, the effect on mixture was additive, so not synergistic. Similar effects, more borderline in terms of, let's say, their biological relevance, were also observed for some sexual maturation index, particularly vaginal opening and balanopreputial separation. So overall, we did found, and you'll see a little bit more in Eoin's presentation as well, that first of all, the tiered approach that we use was particularly predictive and useful to go from the top 200 of concern to the top 3. And starting from tier 1, we were able to prioritize compounds that when we tested in tier 2, so the top 10 of concern, showed at least one cytotoxic and genotoxic, and for most of them, both positive signal, as well as other alterations, including kinase cell viability and transcriptome. The pesticides that were prioritized for tier 3 were also showing different effects, remarkably also sex-related effect, because we aimed also to explore whether there might be difference in the response in the two sexes that we tested, including liver toxicity, kidney toxicity, and you'll see more about microbiome and behavioral effects. And importantly, the doses that we use were between the EU admissible daily intake and an OL, so allegedly those that are either considered safe in humans or with no adverse effect in animals. So the effects that we did observe were at what we in toxicology would consider low doses, or certainly doses that previously did not show any effect. So the new indicators that we use were certainly informative, but we also, as we should do as scientists, had to acknowledge some limitations. So certainly might be ready for more information related to hazard, but more complicated to be used in risk assessment, or even more in preclinical assessment, pre-market assessment, sorry. Indeed, the tiered approach proposed by the guideline was successful in our view, because it allows to prioritize both in top 10 and top 3 risk tested in vitro and in vivo pesticides that actually show to be with positive signals. And importantly, and differently from what you heard from our colleagues in ecotoxicology that were also in VP4, we mainly found additive effects, so non-synergistic. It's too long to discuss this, but let's say that one of the things that we consider is that the closer the target species to the target species was the tested species, the more we saw synergistic effect. And as you can see, as you saw, a lot of the ecotoxicology show synergistic effects, while when we moved, let's say, far away from the target species, we had more consistently additive effects. And therefore, we can certainly conclude that the component-based approach was predictive and useful. It was very relevant to use both sexes. It was very relevant to start from prenatal life to understand the effect of early exposure, which are most definitely, developmental age, one of the knowledge gaps that we often have when we aim to assess the toxicity of substances, but actually very, very remarkable for public health. So with that, I conclude, and I leave it to Eoin, and I also thank my colleagues that are online from the Ramazzini Institute that contributed to this, along with the other colleagues from Sprint. Thank you very much.
How are we doing for Eoin?
Yeah, I'm here. Can you hear me? I actually have my slides, I've amended slightly. Can I share screen or not? Can you see that? I'll turn on my video as well. So is that all good? Can you see the slides on the screen? The ones I've shared? Yeah? Okay, good to go. I can't hear anything really now, so I'm just going to move on. Just first and foremost, thank you so much for giving me the opportunity to speak on this, which I think anyway is a very interesting area of research. It's to do with the microbiota gut-brain axis and our role essentially in Sprint Project on assessing pesticide exposure and influence on the microbiota gut-brain axis. So as Daniele said, a lot of time and resourcing and help was put into this particular part of the Sprint project. So just like to recognize Dr. Reid Matsuzaki, who was a PhD student during the project and is now a postdoc and working in America. So a lot of the work was undertaken by her and under the stewardship of Professor John Crine as well. So I guess just by way of overview, our research kind of veers a little bit away from the more classical toxicology tests. Focus on the gut microbiota is part of the new Sprint indicators, which are new models, as Daniele said, that could be of interest to risk assessment, but are currently not yet embedded in standard guidelines. So the gut microbiota is indeed integrated into this global health risk assessment toolbox, part of the project, as a novel indicator of indirect or long-term pesticide effects. And indeed, Sprint new indicators emphasize multi-endpoints, focused on cross-species assessments and closer to potentially realistic exposure scenarios being expected to result in more solid and accepted evidence-based information for risk assessors. So just to give a background really on the microbiota gut-brain axis and the relevance for human health and the influencing factors that shape it. In our lab in APC microbiome in Cork, we focus on this area in terms of human health from diet, from stress, and so forth. And the gut microbiota itself, it refers to the trillions of microorganisms, so bacteria, viruses, fungi, protozoa even, that live in the gastrointestinal tract, primarily in the colon. And it comprises of over 1,000 different species of bacteria, with each person having a unique microbial fingerprint. So we kind of often refer to it as the second brain. It actually weighs as much, if not more, than the brain. And you have sayings like, you know, gut feeling, gutted, butterflies in my tummy, and so forth. So it's always been considered very important in terms of human health, but we're recently digging down deeper into the mechanism and kind of understanding how the gut microbiota is actually shaping human health and behavior. And although the gut and the brain are anatomically separated, there are several pathways in which the gut microbiota communications happen. And some examples of these, this is a publication from our group. One example is the vagus nerve, which is essentially a communication highway. It's a link between the gut and the brain. It sends signals between the two, and it's very important and is moderated by gut bacteria. You also have the immune system. So the gut bacteria affect your immune system. If you might be aware, they're very, very strong moderators of this. You know, there's important proteins called cytokines, which are crucial for cell signaling, particularly within the immune system, and they're messengers regulating growth, differentiation, activity of various immune and blood cells. And you also have neurotransmitters and neuroactive metabolites. So some examples would be GABA, which is gamma-aminobutyric acid, a neurotransmitter in the central nervous system, plays a crucial role in regulating brain health, activity, promoting relaxation. Serotonin, which is the happy hormone neurotransmitter, plays various functional roles, including mood regulation, sleep, appetite, and over 80% of serotonin is actually produced in the gut. And there's multiple other examples as well. Just considering the factors that kind of shape or implicate effects on the gut-brain axis, obviously our diets, genetics, mode of delivery, how we're born, drug exposure, exercise, but obviously of highest concern in terms of our project is the environment. So environmental chemicals, pollutants, pesticides have a negative effect on the gut-brain axis itself. There's a lot of evidence to show this fact, that pesticides impact the gut microbiota. You know, the trials of the bees as well, well known at this stage, and a lot of these studies have been undertaken on insects and on animals and in the environment, showing extensively how pesticides negatively impact the structure and function of the gut microbiota. And also, when it comes to behavior, there is strong evidence to show that pesticides negatively impact behavior, primarily done in animal models as well. But essentially, these have been undertaken with levels far above what we'd expect to be exposed to. So when we're looking for kind of mechanism, understanding if they have an effect, these levels close to more toxicological limits are used. We kind of summarized a lot of this in a review we did recently, pesticide exposure, microbiota, gut-brain axis. And stemming from this, then we kind of wanted to investigate in our studies, can we expose, can we have an exposure of pesticides far below toxicological limits? So what Daniele kind of mentioned, the acceptable daily intake, the no observed adverse effect limits, can these relatively lower environmentally relevant limits still have a negative effect, not only on the gut microbiota, but on our behavior as well? So in our studies, we use preclinical animal models. So the question you might ask right away, why animal models? Why not just go straight to humans? Well, there's a lot of factors behind why we use models. There's a different array of preclinical models, all the way from C. elegans, which is a worm, Drosophila as a fly, zebrafish, and then murine models, which are mice and rats. And mice and rats are very important, not only because they share a lot of our genes, a lot of our genomic blueprint, so over 80% of genes are shared between mice and humans, but they allow for very strong control of our experimental conditions, which is very important when you want to dig down into mechanisms and causation for what's actually happening. And what's causing negative effects through exposure. And so we have control. As I say, we can dig more into the kind of mechanistic insights. So we can sample tissue, brain, and everything to kind of have a molecular understanding of what's happening as well, not just at a behavioral level. And for the context of this kind of presentation, I'm going to focus really just on a couple of key outcomes, and one was our glyphosate study. So glyphosate, I don't need to explain what it is. Everyone's aware of what it is, and it does and has been shown extensively to have a negative effect on the gut microbiota in our bodies. It's actually been patented as an antibiotic, so it comes as no surprise. But it has also indirect effects on our behavior and overall our health. So we undertook a study with a single glyphosate exposure. So I know it's formulated in Roundup and other pesticides with other synergists and everything, but we wanted to really just focus on glyphosate itself in terms of digging down into what negative effects it can have at environmentally relevant doses. So we did this study over a course of 8 weeks. So we did this in male and female mice. In this presentation, I'll just focus on the results from male mice because of the behavioral phenotype that we recorded, which was not recorded in females. And I can follow up with any queries you might have on that after if you want. But you can see the groups. We had a control group with no pesticide exposure, no glyphosate. And then at the ADI level, and also by 10 and by 100. And this ADI by 100 exposure level is the EU NOAEL, sorry. We did a lot of behavioral tests at the week 5 mark. Now, it might seem quite a short study, but remember, mice age a lot more than we do. 1 week of a mouse's life is about 6 months in ours. So this could be potentially deemed to be a subchronic exposure study. So we did a lot of behavioral assessments at 5 weeks of exposure. And I just kind of want to focus on one behavioral result that we got, which was very interesting, which was a behavioral test on social behavior. We also took samples for the gut microbiota at the end, and we took brain samples and we did gene expression analysis. But just focus on the behavior for a minute. So the social behavior test, so this is a 3-chamber social novelty test. So essentially you have the test mouse, which is in the middle, and the kind of first main stage is a mouse, a conspecific, so a mouse the same age, same sex, is placed in one chamber, and an inanimate object is placed in the other chamber. And the mice has a period of time, 10 minutes, to interact with either the mouse or the inanimate object. And then after that time, the inanimate object is taken out and a new mouse is put in. So that's the novel mouse. So typically what we would expect to see in a behavior like this, if you focus on just the white bars, which is the output from the control mice, is more time spent with a novel mouse. So this is the classical phenotype that we'd expect from this behavioral test, which we did see in the control no glyphosate exposed animals. Each one of the circles represents the time spent in the chamber for one particular animal. So if you look at the glyphosate exposed animals then from the ADI to the NOAL, you can see for the ADI group, there was a significant difference, which we would expect. So no negative effect on glyphosate at the ADI level. But you can see above the ADI and at the NOAL, we have a perturbation, a negative effect or a disruption in social preference. So this was quite interesting. It has been shown in other studies before at higher levels, higher exposure levels, but we were able to kind of confirm the phenotype here at these exposure levels. So what it does is, this is what it says, and then we kind of looked at the gut microbiota. So in the same animals, we actually characterized the gut microbiota in each of the samples. So this is just an example of the composition. So this is stacked bar plots. So each color in this plot represents an individual, a group of microorganisms. This is clustered at the family level. So and each vertical bar represents the microbiome of one animal. So you can see we have 10 or 11, I think 11 in the exposure group, animals here, and their microbiomes kind of illustrated. If you can just focus on the lime green color, this represents the relative abundance of the Lactobacilliaceae group. Lactobacillus, you probably all heard, is quite, globally recognized, being used as a probiotic. Generally beneficial for gut microbiota and healthy human functions. So you can see a significant reduction in relative abundance at the NOAL group here in the majority of the animals. And this just illustrates it further. These are box plots, so relevant abundant box plots, so higher in the y-axis means a higher relative abundance. If you just focus at the control group, which is in gray in these figures, and the kind of opaque purple blue color, which is the NOAL, so you can see a significant reduction in a lot of the Lactobacillus species comparatively to the control, which we found, I think, close to about 10% of overall Lactobacillus species were significantly reduced at this glyphosate exposure level, which is a really interesting finding. And we asked the question then, does this disrupted microbiota have a role in social behavior? So is the microbiome having a part to play? So what we did was we took the microbiome, so the fecal matter comprising all the microorganisms of the control mice and also the perturbed glyphosate exposed mice, and we actually transferred them to naive mice. So mice had never been exposed to glyphosate. This is just an overview of the experimental design. It's done over a period of weeks where we semi-continuously expose the mice after antibiotic kind of reduction of the native microbial populations to these mice before sampling, and we did behavior analysis as well. And just to focus on the social behavior again, we found that the phenotype, so this disruption in social behavior, was actually transferred in the microbiota. So the FMT from glyphosate exposed mice, the mice that had no exposure to glyphosate, suggests that the perturbation or perturbed microbiome can mediate alterations in social behavior, which is quite a striking finding. We also looked at other pesticides of concern, so tebuconazole, the fungicide. This had an effect on social behavior even at the ADI level. So it was only at the ADI, not at higher exposure levels. It also had an effect on key tight junction proteins. So these are proteins that are involved in gut permeability. So you might have heard the term leaky gut before, which is a consequence of many factors, including drug exposure, environmental pollutant exposure. So this is something we found quite significant in tebuconazole exposed animals. So this may compromise gut barrier integrity. And then for acetamiprid, no significant perturbation in social behavior, even though close to significance in close to non-significance in the ADI group. But we did find a little bit of interest in terms of gut barrier integrity. But what we did find was a decrease in MC1 levels, which is immune indicators. So this might imply kind of negative effect on the immune system. So we also looked at through the Ramazzini study the mixture. So those were individual pesticide exposure studies, but we did focus on the mixture through the Ramazzini exposure study, which was a more long-term prenatal exposure study. So a different experimental design in terms of timeline and exposure, but the same doses used, and also individually, and included the mixture of all three pesticides of concern. Just focusing on the glyphosate and mixture again, just to give an example of the exacerbated effects of the mixture. So the number of differentially abundant taxa was increased or exacerbated by the mixture itself. So you can see each one of these numbers refers to the significantly different microbial group comparatively to the control. So even at the ADI, there was far more altered microbial groups in the mixture compared to the single treatment of glyphosate. And we can actually visualize that in a beta diversity plot, which is essentially how the community composition looks in a two-dimensional space. So the closer each of the icons are together, the more similar they are. So the white icons are the control group, and the colored icons, so the glyphosate is in blue and the mixture is in red. So what I hope is coming clear here is that the red cluster group, which is the mixture, the microbiome of the animals exposed to the mixture, are further away from the control group at the ADI level, which means a higher dysbiotic effect and a change from normal homeostatic conditions in the gut at the ADI level for the mixture compared to the ADI. And we looked at function then, which we use gut-brain modules as a typical functional indicator. These are pathways that are known to have molecules and pathways of importance in terms of the human nervous system, so that neuroactive compounds like tryptophan synthesis, kynurenine, and so forth. So what we found was the single exposure of glyphosate had negative effects at the NOAAL level, which are indicated in red. So red means a kind of a suppression, a reduction in the neuroactive pathway. So red is bad, essentially, and blue is good. Blue-purple is good. So you can see definitely when it comes to the higher level of glyphosate exposure, there's a negative effect. But I hope what's coming through here is that at the higher level of the mixture, there's a far more robust negative effect on key functional pathways in the gut comparatively. So yeah, and this just kind of highlights what I said. So just to summarize, glyphosate exposure at or below the no observed adverse effect limit not only alters gut microbiota in male mice, but it leads to social behavior deficits that can be transferred via microbial transplantation. And this highlights and underpins the microbiota's role in pesticide-induced neurobehavioral effects. A combined pesticide effect is there. So the mixture of pesticides exert negative impacts on the gut microbiota structure and function that exceed those of individual exposures, highlighting the importance of evaluating these multi-chemical exposure scenarios. So we recommend broader risk modeling. So supports an expansion of the EFSA's current pesticide risk assessments to include microbiome health in long-term low-dose exposure studies, and the need, obviously, for human intervention studies, longitudinal human cohort studies with microbiome profiling and neurocognitive assessments to kind of get more into the full impact of pesticide exposure on the microbiotic gut-brain axis. So, thank you.
Lovely. So I'd just like to thank our panel and Eoin as well, who's obviously remote from us. We are going to move on to a little discussion in a moment. I'll just also point, I was going to point to Amanda's illustrations that are just off to your side if you want a little confirmation. And just to recap with all of our speakers, to thank all of the human volunteers who took part in these studies, and also just to emphasize to everybody that all of the animals were kept under the ethical and legal supervision that we would all expect. So, you know, that's all been taken care of, but we didn't necessarily mention that at the time. I'm going to ask these gents to stay on the stage because they're next after Lindsey comes to do a short recap, and then we'll move into a panel.
All right, I'm back up here. Oh, it's loud. Okay, so thank you so much to the human health presenters. A lot to cover there, but I want to briefly pull out some of the key messages that we can express for policymakers. Let's just go through this again. Sorry. Yeah, so here we've talked about human health risk assessment and also implications for monitoring. In thinking about our risk assessment at the pre-market stage, we heard from Daniela primarily and also from Eoin about the testing that is required. And so following Owen's presentation, we can think about areas that can be strengthened in the PPP and active substance assessments. So stronger neurotoxicity screenings, including animal social and behavior tests, could be enhanced. As well as looking at microbiome changes and whether relevant testing can be built out in the future versions of the data requirements. Also to continue to account for more early life stages and vulnerable populations in testing, particularly in the types of experiments that are pulled from academic work and in the risk assessment process. And again, coming back to mixtures and strengthening the testing of mixtures, especially when we're talking about mixtures that are recommended for use, like spray tank mixes or combinations. So in human exposure, we heard about the role of non-dietary exposure. And in the current data requirements focus more heavily on dietary exposure, so pesticides from food. And non-dietary exposure regulations mainly focus on the occupational context, so workers and operators, as well as residents and bystanders, but this can, so those who are near farms, let's say, but this can overall be strengthened in the regulation, given that there are pesticides in our environment and that occurrence carries the potential for exposure. We talked about using safety factors as a way to adjust our understanding of what is safe exposure. So adding safety factors in the calculation of ADI, so acceptable daily intake. This is especially to account for vulnerable groups like children or women of childbearing age, as discussed. And also where our testing is missing testing of these vulnerable groups. And then finally, very important, the use of biological guidance values. Paul emphasized this. This is how we can compare samples from human biomonitoring to values that are meaningful in specific matrices, like in urine, feces, or blood. And these are things that can be done when pesticides are being approved and tested. So finally, moving into monitoring, it would be useful to enhance the use of human biomonitoring in the EU, potentially through EU programs They're already coming about in national programs as well, select member states, but this could be a very powerful way to begin capturing exposure from, let's say, all routes and sources of uptake, and in some cases, identify an exposure hotspot or potential, let's say, breakthrough, despite all the good efforts that farmers and operators make to keep exposure to a minimum. And in that, there's also an opportunity to use biological guidance values in our policy, so across EU bodies, and also potentially in laws setting legal limits for what can be detected. Okay, so we rushed through that. You can also just see our deliverables later. I'm going to invite our panelists to the stage, and together with Matt, we're going to lead a short panel. If I understand, we will be going into lunch a little bit, but I hope we're okay with that. All right. And I forgot, so after lunch, we'll also talk more about how we scale up the impact of these kinds of data. Okay, come on up. Is this everyone? Am I missing anyone? Do we have Maria online?
Yes, I'm here. Hello, can you hear me?
We can hear you, and let's see if we can adjust it so we can see you as well. But if not, please. There you are. Great, perfect.
Hi, hello. Thank you.
Yes. Thank you very much. So I will not introduce the speakers who have already been here, but there are microphones on the table, so those who are just joining, please introduce yourself.
Yes, it's working. My name is Jacob van Klaveren. I work at the National Institute of Public Health in the Netherlands, which is close to regulation, but which is not a regulator itself.
Maria, why don't you introduce yourself?
Yes, hello. Thank you for the invitation. My name is Maria Anastasiadou, and I'm Scientific Officer at the Fitte Contaminant Units at EFSA. Thank you.
So I will begin with a prepared question, and do I understand correctly, we are taking questions from the audience? Yeah, so I'll wait for that. So just a general question to get started with the whole group. What are the biggest gaps in our understanding of pesticide risks to health and the environment? And how can researchers address these gaps? And Shah, go ahead.
Well, I think congratulations with the park results, because they are really impressive, and you see certain areas where it can come quite soon to regulatory considerations. Implementation is to the regulators. I don't know how that goes, but you see human biomonitoring, it's harmonized everywhere, but you're now asking what needs more research for next projects or whatever. And I think you showed also a lot of endpoints that are now starting to come up and that are a little bit farther away from regulatory implementation, because we first need to understand, like the neurotoxic endpoints, they might need more research, like Parkinson's diseases, and these types are not also included in mixture considerations yet. But EFSA has established a reasoning and a methodology for that, but not with these endpoints. So these endpoints are new. They need test systems, maybe according to OECD way of thinking, but it also needs more elaboration. Certainly the non-dietary part, that is not well understood, because we don't have a legal framework to generate those non-dietary data. That's coming from sprint projects and other projects. So, but it's an important route. If you see so many pesticides in indoor dust, you wonder how will that get into the body. We don't know. There are so many, but you don't see it reflected so well in the human biomonitoring studies. So what is going on there, we don't understand, but we are worried about it. So more in that area, consideration would also be very helpful.
I would like to add, thank you, Jacob, that how substances behave once they are in the body is also not well understood. I'm referring now to vulnerability of early brain development. So we'd like to know if substances can actually pass through the placenta to reach the unborn child. Also, we'd like to know, also for grown-ups, to what extent actually substances can go from blood into the brain. And then we are touching upon an interesting field where we see some interesting developments, like for acetamiprid and other similar substances have been shown to be entering the, what they call, I think, the brain fluid. So there are two papers at least, one small paper and another large paper showing that actually those substances are found in the brain fluid. So that's, I think, indicating that we need to understand what type of substances do that, and that we have also the modeling frameworks, let's say, adapted to those gaps in the future.
May I hand over to our guest, Maria? Would you like to make a comment now?
Yes, thank you. So maybe complement, I would, because I understand that your question is about research projects, so and a little bit about what Yann was discussing previously on how we can link, in fact, the research and development activities with within a regulatory context and the risk assessment. That it's the risk assessments that are fit for purpose. So in this case, it might be relevant as well to focus on NAMS and maybe to develop AOPs and mostly validate this in order for EFSA to be able, in fact, to integrate them in the risk assessments. Thank you.
Thank you very much. We can continue with our.
Okay, also to. The other one. That one is working also.
Also to complement and more focus on an environment, one data gap, of course, is related with mixture toxicity. And I think we made a very good contribution on Sprint, but we really need to generate more information and include in retrospective risk assessment to include the mixtures. Also long-term studies. Most of our exposure are short, little, so we have to extend the exposure time. Also to understand the environmental fate and the effects of metabolites, not just the active ingredient. And there is a huge gap on this issue. And maybe we should also Sprint is contributing to integrate environment and human health as a global health or one health approach, but is quite challenging to interlink both dimensions, the environment and human.
So just to add a comment on what we already heard, and starting from Nelson's point that we really try to tackle with Sprint more of a One Health approach, and you can see that also there are borderline models like zebrafish, which are relevant for ecotoxicity, are also informing and useful potentially for hazard assessment for human health. So how to make a coherent interpretation of all this, it's also a challenge, but it's also for sure a resource, as we saw, for example, in the results that he had for zebrafish, which we included in ecotoxicity, but they are not less relevant or interesting, of course, also for the human perspective, human toxicology perspective. I think we have also to understand the limitations that derive from the experiments that we did. First of all, we cannot test endless number of chemicals in mixtures. Then we have limitation intrinsic in the models, like in vitro, indeed are becoming more and more useful to anticipate cytotoxicity or genotoxicity, but they cannot explore prenatal effects or reproductive developmental effect or endocrine disruptive effect also, apart from certains, are really difficult to be explored there. So the tiered approach that, for example, was suggested by EFSA guidelines was very useful to try to do that only needed experiments based on some early warnings or signs, let's say, from the in vitro data on outcomes that we cannot actually test in vitro. And the prenatal aspect, I think it's key. It's in line with the developmental origin of health and disease that I would say, all agree with now, both at the European and global scale. And so the more we can adapt our models to what is already and continuously more demonstrated to be the most detrimental, so the early exposure, the better.
I just want to add one thing on this, which is in Sprint, we have a lot from the toxicological side of the coin, but it was mentioned in the beginning by Isabelle Baldi. A lot of these outcomes with already some stronger intermediate evidence. A lot of the determinants that lead to these outcomes, exposures, is not just pesticides. So one thing that I also think, especially for the global health that Nelson just mentioned, is to actually also go more into epidemiological studies, where you can look at pesticides in combination with other exposures, and then different health outcomes across the population, adjusting for smoking status and other things.
Are there any audience questions specifically for the panel? I have prepared questions as well. Isabelle? Yeah.
Not working. Well.
Here, I come to you.
Yes, thank you for all these presentations. And of course, it's a real improvement to see what we can deduce from the combination of pesticides in your models. But my question is that it's not exactly the same in humans. You don't have really a cocktail at the same time point. You have time is running between one exposure to another one. Is it something we can extrapolate from your results? Because this time point is, this time thing is essential for me. Because in the whole life, you will have several exposures, but not at the same time.
I think that's more of a human health question. So let's start here.
Yeah, I think it's a good question. Actually, let's say we're trying to do that in exposome, where we try to assess, let's say, all the environmental factors over life, the complete life cycle. So I'm not personally involved in exposome, but I think that the idea is very good to look at, let's say, the whole life cycle, let's say, starting preconception, let's say, with the parents being exposed. And I think there are certainly for pesticides some challenges there to look at that. So I'm very much in favor of organizing studies amongst maybe farm families where the parents are involved in actually applications, and where also we can also study offspring and collect data. And I think that we need also the help for modeling there, because I think you need to collect a lot of data, but to start, I don't know, Daniel, if you think that it would be good to start a cohort study in Europe, maybe, also because we are listening to findings in the US, but we're wondering how relevant are they for Europe, so that we should have a discussion, at least if that would be feasible.
I just want to add to that on this, let's call exposure frequency duration discussion for pesticides, that not on this project, but I'm aware of other projects that of development of what we're calling exposome scenario generators, where you can, for certain pesticides, based on application rates, type of crops, actually map what would be the peaks across the year, and then try to generate at least relationship between exposure time. I think we're getting there, but it takes time.
So just to add something on the question, of course, when we do the modeling, especially in toxicology, you generally try to simulate the worst case scenario, which is, starting the exposure from early life. And it's a fair assumption to assume that the earlier you start, the more detrimental the effects. So effects of exposure that occur later in life might give only less. So our perspective is that, if anything, with toxicological assays, we might underestimate the risk. We hardly overestimate the risk. And the factors that I mentioned during my presentation also account for the different sensitivity amongst different people and the translation from human to, from rodents to humans of the results that in part should account for these uncertainty factors that I'm not sure that we can really address one by one in different experiments, but rather acknowledge as uncertainty factors that we have whenever we apply toxicology to the human scenario. But certainly a person that smokes and is exposed to asbestos and is exposed to other carcinogens is more likely or more prone to have then more effects than if he was not affected. But unfortunately, we cannot test all these hypotheses because of the 90,000 plus chemicals that we are exposed to, so very wide and different scenarios.
Yeah, and let me say that the same is valid for environment. We just test a single exposure, but in real environment, we have multiple exposure. As a case study leader in Portugal, in vineyards, farmers usually, they apply pesticides every week. So by spray application or later by rainy events, we have multiple exposure. And yeah, is something, there are studies that are testing and assessing the multiple exposures, but just one or two compounds. But yeah, is an important issue, yeah.
It was this morning said from EFSA, it's not only one project that makes a difference. There are multiple projects that needs to come together. For example, in the Exposome project, like the Athlete project, you have measured people in different time frames, also before they were born, or at least the mothers. And they looked over time, what are the effects? So that's a more a longitudinal study with effects. And both should all those things should come together, like SPRINT, but also PARC. And the good news is indeed that even in the parliament, all those people go to the parliament and say, we need to do something in the future on this. Human biomonitoring should have the future in this area. Related to the mixtures, indeed, you prove, and all those studies, they prove mixture effects exist, and we need to do something in the regulatory process. But you can only do something on single chemicals. So we also need to understand which of the pesticides form a mixture with the same endpoint effect. And that's now done by EFSA to group all those pesticides in assessment groups. And then understand which of those pesticides are really driving the risk in mixtures. Because if that's a big driver, you can restrict that pesticides or ban that pesticides, or you can enforce that pesticide exposure route better. And that's how you can tackle the mixture problem. It's not all the individual mixtures and the different mixtures everywhere. No, it's the pesticides that grouped that make a mixture and that you can restrict in regulation.
And I just want to pick up on one thing you said. You talked about identifying the components that are driving the toxicity or the effect, and that's a theme we'll hear about this afternoon. So I'm targeting our efforts. I want to make sure we don't forget our online panelist. From the EFSA side, any comments on this question, multiple exposures, and how to account for this?
So indeed, EFSA has done a lot of work towards this direction with the cumulative risk assessment of pesticides. But of course, we have from one point the assumptions, and we hope to build more realistic scenarios indeed for the combined exposure. But also using the potency factors in the assessment, which indeed has not been considered, I understood from in the presentations that were done previously. So I think that the human biomonitoring data could give a very good insights, in fact, on the exposure to different chemicals and the prioritization, and taking, of course, into account all the limitations and whether one measurement can be extrapolated to chronic exposure. And but what it is important, I think, is to integrate all the lines of evidence in order to be able to build scenarios that are more realistic. Thank you.
Thank you very much. I think we have time for, so we have time for one more question. Go ahead, Abdallah.
Yeah, thank you very much. Yes, I have a comment about the toxicity versus risk that you presented. I think, as we discussed many times, is very interesting, but there is some limitation that was also mentioned before. It is relative to the DPA analysis, And also, coming back to the comment of Isabelle, we have to take into account the long term. It means that we have some substances that are already accumulated in some tissues. And if we add this DPA, maybe we will have some other these on the substances in other places in your graphic. And maybe for me, it will be useful to mention that this analysis is relative to the DP analysis.
Yeah, so we carefully started to do the duplicate portion analysis. I should explain maybe for the audience what it means, you know. So let's say if you participate in a DPA study, you have to imagine that if you have a family with 4, that you have a guest. So you put a chair at the table, and then you put there a big bucket, okay? And if you are going to have dinner, you have to prepare 20% more, and then you will just, everybody's participating and has a plate, and then what is on the plate of the guest will be dumped into the bucket, also the drinks, the beverages, everything. So that is about how it will be done. So I think that it is for research, it's good. I think to test also, are we on track? Let's say with our assumptions regarding how people prepare their foods, because we are only looking at the commodities, how they are sold in the retailer, in the supermarkets. So it's good to test hypotheses regarding maybe some uncertainties or variability that we don't know. But I don't think it's feasible to do this in routine. So I think that it's good that we tried in a small study, 43 participants. But I think maybe you could ask the participants how they liked it. But it's rather a big burden for people to participate in such studies.
I'm just doing a little editorial intervention. So we'll just hand over to the lady over there.
Hello. Yes. Hello. I'm Angeliki from Pesticide Action Network Europe. So thank you very much for this amazing piece of work. And I think what's really important here is that we are coming closer to what's the real data, no? What's happening in reality, as close as we can come. And the problem I see clearly is that although we have a pesticide law, like we have a regulation that says that pesticides that they are in the market should cause no harm to human health and the environment. And we also have that mixture effects should be taken into account. So I think what I see is, and you know that because you mentioned it, that you clearly show the shortcomings in the current risk assessment when it comes to pesticides that allows these chemicals to be released, that we all exposed to them, neighbors, consumers, not just the farmers, and so on, even organic farmers. So I see 2 lines of action. One is that you already mentioned we need to incorporate this into risk assessment one way or the other, whether it's AOPs or going through OECD way of thinking, like you said, but we know that this is going to take many years. It can take 10 years, 15, 20 years. And I think that your data, they highlight an urgency to act. You have acetamiprid, which is toxic to neurotoxic, and we are all exposed. It seems like there's a high exposure. So one line is to what we do now with what we have. Are you planning to go to regulators to say, take stricter actions on this? We have glyphosate, for example, like the most popular herbicide. And there is also the background levels. We see like really old pesticides are still there. So this is not taken into account when you're doing a risk assessment of an active substance. And this could be addressed with an additional safety factor, like you said. So these are faster solutions than going through the, trying to understand exactly what's going on and which is like the main dominator that links this mixture effect. And we can do that because we also have the famous precautionary principle, which we could use it in order to be politically active before we go and see really, really adverse effects in human population. So yeah, my question maybe is what's your short-term action and yeah, in your long-term? Thank you.
So I think that, let's say, there was a kind of surprise to us in when we were studying when we're doing our human volunteer study on cetimiprid, that when we were doing that study, EFSA announced that they would reduce ADI by a factor 5. And then I looked, let's say, into the report, and Maria probably knows that actually they said because of a gap in knowledge and because of a concern for developmental neurotoxicity, so development of the brain, combined with, let's say, information that actually the substance can go from the blood to the brain, they decided to take action. So that, I think, is a good example. So I wonder now what will happen to glyphosate. Will authorities wait until 2033? That's, let's say, agreed re-evaluation. So, but I wonder, let's say, what the impact of research will be. Of course, we have to see some papers have already be published, like the cancer study, but also, let's say, the study that we heard about today is still under review. So, but yeah, I think I'm not the person to answer the question, but I think it's a good point that you are referring to, let's say, do we have to wait to have, let's say, convincing scientific evidence, or can we already expect authorities to act earlier? So that's your question. So
yeah, I think it's not as black as white. So it's the case that quite a lot of things happening in mixture regulation as well, but it's only limited to dietary exposure at the moment. And secondly, we have things that we know today and but might need further exploration before we know it for sure tomorrow. So that comes later if you have evidence for that. But certainly a lot of things on mixture regulation is ongoing. As stated in the pesticide regulation, it should be done as EFSA has the methodology agreed, but it's limited for dietary exposure at the moment. So what we try to do now is also to explore how much is the human biomonitoring data from SPRINT away from dietary exposure. Do we see the same chemicals in the mixture risk assessment using HBM studies or dietary exposure studies? If so, then it's maybe covered by dietary exposure. If not, then might come from non-dietary exposure routes, and that's not covered yet in the regulatory process. But maybe by showing all this human biomonitoring data, it could be a better way forward to have these studies all over the place and say what is then safe for people from all routes of exposure. And that's also in strategy, but it's also showing by all the good data you have explored. Still, human biomonitoring data is not complete. It does not cover all the pesticides, but quite a large number. And also there you can proceed with more pesticides to be included in human biomonitoring, especially the ones that we also see in dietary exposure. Not all of them are in human biomonitoring yet. But it's going into the right direction. It's certainly the case that things are being implemented now, but only for dietary exposure. And we can extend that with all the beautiful human biomonitoring data from SPRINT, hopefully in years to come.
Thank you very much. We don't have time for many more comments, but I want to make sure we hear from our regulator, from Maria.
Thank you. Sorry, just a risk assessment rather than regulator. I'm not a regulator. So just to say that indeed, I see that EFSA responds and prioritizes the substances that are of concern. I have not worked on this specific dossier, so I cannot, but I just echo what you just said. But that just also, we always receive mandates if there is a concern of something, so to reevaluate in general, not only in pesticides, but in general in EFSA, in the area of contaminants, for instance, that I'm working on. But I just wanted to say also that the data that were presented, especially when it comes to the monitoring results, are quite limited. This has already been expressed by the different presenters today. So it is very important to take this insight into consideration and the limitations that this incorporates. Of course, also to highlight that in the pesticides area, as already been mentioned, we do not only consider the dietary exposure, but also the exposure for the people that live in the surrounding areas, not only the farmers, but people that the bystanders, etc. And we also consider the dermal exposure, the inhalation. Of course, there's still room for improvement of the risk assessment. You mentioned about the exposure to dust, and this is something that needs to be considered in the future. But just to say that there is, especially the assessment of pesticides is very, very thorough, and it is very regulated. So, I mean, yeah, there's a lot of work that is done towards this direction. And for sure, I believe that the chemical strategy for sustainability, the implementation of the one substance one assessment will solve a lot of these issues that we're discussing today, especially when it comes to the aggregated exposure from all sources for the substances. Thank you.
All right, with that, I think it's time for us to have lunch. Yeah.
Thank you to the whole panel. Thank you very much. And thank you, Maria. Just to say, let's grab some lunch. We'll come back at 2 o'clock. Just to remind you, there is a poster competition, and we need you to have a look at those posters. There is a massive, a huge, a life-changing prize, I'm promised by Jane, for the person. That's what she said. There's that sort of prize available for the poster competition. There is opportunity to vote for what you would like in future research, and you'll find that on your tables and in your magazines. Thank you so much to our panelists. Thank you so much for your attention and participation this morning. We start again at 2. Thank you. Okay, everybody, let's start again for our afternoon session. If you'd like to find a seat, Jakob is just waiting online for us. Just to say to our friends online who've been asking a lot of questions, more questions than we've been able to deal with, that we will save those questions and get back to them individually. Somebody from Sprint will reply. It's been very lively online, lots of lovely questions, and we haven't been able to realize those in the room. So this afternoon, we are going to go to the toolbox, and Jakob is just waiting for us. And then we're going to go to the farm, excuse me, and talk about some success stories before we have a concluding panel. We're going to finish this afternoon fairly promptly because everybody needs to be somewhere else. Lots of journeys heading home. And even if you're not heading very far, you probably still want to go home. So we're going to be finishing fairly promptly this afternoon, and we'll try and bring it all in on time. So I'm going to hand over to Jakob, who's online. Over to you, Jakob.
Okay, good afternoon, everybody. I'm very sorry that I cannot be there physically, but we have state exams yesterday and tomorrow, so I could not handle. Welcome on the afternoon block, and we would like to start with a presentation of the one of the final product of the Sprint project, which is the toolbox, Global Health Risk Assessment Toolbox. That's one of the final products that will be released at the end of the project. And as you can see, many names here at the first slide, but even more names were participating and contributing because basically every work package was contributing to this work package. So what is the toolbox? What is the Sprint toolbox? It's basically the set of different tools that we try to concentrate on one place. And the toolbox is integrating all available data generated by Sprint. So the data from the case studies that you could see today, existing databases and literature that were not produced by Sprint, but we are using this data to do some new exercises and models and estimates. The data on PPP exposure, but also the data on PPP effects. So from all the topics that were addressed by the Sprint project, and all that stuff collected on one place should basically result in integrated risk assessment, modeling and mapping of risks and impacts of the PPP mixtures at different levels. So we try to go from the local to pan-European level, and what this toolbox is good for. So we really believe that this toolbox will help with all the other tools that are available from the other projects and other researchers to the policymakers and decision makers to make really informed decisions based on the real data and the real evidence. But of course, we believe that these tools will be also very interesting for scientists, but also for the educated public. So these are the user groups that we are targeting the tools for. So the toolbox basically is a website still not publicly available, but I prepared a few screenshots for you with all the tools publicly available. So you can expect that at the end of the project. So there will be the overview of different tools, what they are good for, and then just some taste for the tools that will be presenting the case study results, the modeling of environmental concentrations, the estimates of the ecological risks, and dietary exposure, and many other tools. So in the rest of my presentation, I would like just to quickly describe what the main tools are capable to do and provide. So the first tool will be the interactive presentation of all the Sprint collected and generated results in the case studies, as you could see the presentation in the morning. So all the overviews of and comparisons of different countries, different matrices, different substances, in a very intuitive and easy to interpret way for everybody. Then a set of the tools, so not just one, but several of the tools, are basically following the concept of the risk assessment. So this is what we call Toolbox Core. So it's starting with the estimates of the inputs and emissions into the European environment. And we base that on a large data that are available in European countries. Then we try to predict what will be the consequent environmental concentrations and what will be related exposure to either ecosystem, targets, or human. And then we try to couple these with the effects known of these substances and of these mixtures, and to derive the ecological risk, and also for some example data, the impacts on human health. So these tools, these major tools of the toolbox, will be good to design the future strategies for pesticide reduction. So the idea is that you can, for example, see the temporal spatial accumulation of certain substances and related risks. So then you can do the informed decision that by withdrawing, you can reduce the risk of the mixture significantly, or you can decide that, for example, spatial accumulation of certain crops is not good because this brings some accumulation of specific pesticides that together are quite hazardous mixture. The other use of these tools can be targeting monitoring campaigns. So we can, for example, set the areas where we expect, let's say, again, accumulation of risks or higher concentrations based on the occurrence of the crops and plant protection products that are used typically for these crops. So we can also identify the priority areas for management interventions. We can also investigate optimal mitigation strategies, because in the models, we can do the simulations, changing the pesticides mixtures used for certain crops, or replacing one product with the other one with different hazards, and so on. So we really believe that these tools will be good for the policymakers and decision makers to play with. I would like to enlighten a bit the way how we do these pesticide inputs modeling. So we are starting with the tool which we call generalized application patterns. This is actually the typical application of each substance for a certain crop, with defined application rate and BBCH and maximum number of applications. With that, we are able to characterize for each, let's say, virtual field, how much is going to enter the environment. And then we are using the spatially explicit models to predict the concentration which will be in the topsoil and the concentration which will be in aquatic ecosystems. So using this usage data and data from the national registers of plant protection products, we are producing so-called GMAPs, which are the generalized mapped application patterns. So they are showing individual fields within the region, and they are showing how much gram per hectare of each active substance is entering the environment. Then we apply the models. So we use the models for soil concentration. So we basically use the quantity of active substances and can calculate the topsoil layer concentration using the crop interception factors from EFSA, soil bulk density, and application rates. The results of this modeling are the initial concentrations of each active substance just after the application. However, we may also, and we do, involve the half-life of the substances, and we calculate the time-weighted average for the field, for example, for 30 days or 56 days, depending on the target exposure that we want to calculate for ecological receptors. For the surface water, we are using much more complicated modeling. So we predict the input to the surface water by surface runoff, and we adopted the approach in which processes are driven by land characteristics, and they affect how much of the applied active substance on a given crop enters adjacent streams. In more details, the concentration in surface water is obtained by taking into account farm-specific active substance loads and basing a specific river discharge volume. We also use the hydrological variables, for example, river basin polygons and river discharge data obtained from the hydroshed database, and we combine that with a country-specific hydrological data, for example, the river network data and cadastre data. So finally, we end up with the predicted concentrations in the rivers. And then this is at the level of the district, actually for individual fields and individual river basins. But of course, we also want to do some aggregation. So we are scaling the data up to whole country. For now, we have done this exercise for Czech Republic, Netherlands, and Denmark, where we can see the districts and typical concentration in the rivers and in agricultural fields in these districts. These environmental concentrations are not difficult to match with the hazard data of each individual substance that we take from the databases, ecotoxicological databases like PPDB, and then we can calculate the risk quotient. So what you can see just on this example, for 3 substances on 2 different districts in the Czech Republic, and you can see individual fields, and you can see the calculated risk quotient for soil organisms. And we can do that actually for all the substances and the whole country as well. Then we model the air concentration. So we have adopted previously developed and verified model that maybe somebody knows, OBO model, which was OBO studied done in Netherlands. And we calculated average yearly concentrations of a given pesticide in air as a result of primary drift during the application and also secondary drift during the evaporation. Then we added the probabilistic component to be able to simulate and also extrapolate for the national scale. So this basically means that we took different climatic conditions and combined them with the most probable application scenarios. And finally, there is calculated average concentration in air, but also some uncertainty, so the possible range of the concentrations. And this model was already calibrated against the 7-day active air sampling data from previous studies. So again, the results are the maps showing the air concentrations for individual countries. Now we are moving to the pan-European level. So it's pretty difficult to use very resolute data to model the environmental concentrations for the whole Europe. So here we use completely different approach. So there is a crucial differences in modeling methods. Here, the tool called PestLCI consensus model is used to predict the pesticide emissions from global pesticide usage data that were available to the team that was creating this within the work package 6. And the result are the predicted distribution of each active substance within the European environment into the air, soil, crop, and water. Then these data were combined with the geospatial Pangea model, which is kind of environmental distribution model, which recalculates these data using the refined atmospheric and terrestrial grids with properties of these compartments into the final result, which are the concentrations in individual compartments, again, in air, soil, crop, and water. So these maps are available not just for the selected countries, but for the whole Europe. Of course, the drawback of this is the resolution and also the approximation, which is very different from the approach that I described 2 slides back. The other tool is focusing on a human dietary exposure. There we again, similarly as with the estimates of pesticides inputs, we were working with the already existing big data. So we used the data for top primary food items from the food basket with the highest percentage of consumers in the whole European Union. And we used the concentrations from EFSA, so the concentrations of residues from the database. And we use the data for the substances that had at least 15 observations and that they had 90% or less percentage of missing data for each food item. So we did kind of filtration according to the quality and quantity of the input data. And then we did some imputations to tackle with the missing data using maximum likelihood estimations and regression method. And then the results are maps that are showing the dietary exposure of the imputed residue concentration multiplied by the food consumption for each of active substance per food item and per year combinations. So the maps are showing the concentrations in the food items, then the concentrations of the daily intake, and finally, sorry, the concentration in the food item, and finally the concentration per body weight. We are also involving some food processing processes, for example, peeling and other food processing factors to tune the estimated values. Similarly, for farm animals, dietary exposure is attempt to calculate the daily intake. However, here we use the pesticide feed intake from our case studies in Sprint. Then using scoping review, we use the body weight distribution per each farm animal type. And finally, we come to the calculated feed intake. Sorry, we use the feed intake again from the scoping review. And finally, we end up with a daily daily intake of individual substances per body weight. The other tools are presenting the results of Sprint. So these tools are not developing any new data treatment. Similarly as the presentation of the case study results, they are just overviewing and presenting in a user-friendly way the results of the work packages that you could see already today in the morning blog. So the results of the toxicity testing that was described very well. This tiered approach with all the results. So that will be also available in the toolbox. And also the results of the ecotoxicity testing that was nicely presented by my colleagues in the morning. And again, in the toolbox on the web, you will be able to access all the results in a user-friendly way for all the testing organisms, and also the conclusions written the way that also not just the scientists, but also the policymakers and wide public will be able to understand our messages. And then we have also the part of the toolbox which is focusing on a human health impact assessment. Here I can present only one of the examples that will be shown there. And this is the study focusing on glyphosate pesticide, and one of the health issue, metabolic syndrome, and then using the already existing data and their meta-analysis, we calculated the exposure response functions, and then we use the data collected for the Netherlands about the occurrence of glyphosate in Dutch adults, and then combine with the other data and calculate it, we come to the end, to the final estimate that these cases of metabolic syndrome are estimated. The number of the cases in the Netherlands is estimated per year. So similar exercise was done also for some other diseases. Then last but not least, the Toolbox website is also containing some information collected during the whole project. So for example, during VP3 activities and during also VP5 activities, we basically met a lot of different fate models. So we considered useful to also present these models in a searchable library, kind of overview of available fate models to utilize our knowledge about these models. So that is another tool. So with that, I would like to come to the end of my presentation. And these are basically the policy recommendations that we also gathered during the preparation of the individual tools and toolbox. Some of these messages are basically coming from the struggles we had because of the situation, for example, with the data availability. So first policy recommendation or key message is that it would be really, really good if we have a harmonized data at the national level. And we mean both for the plant protection products usage, but also the national data of the plant protection product registries, because these data, and we are preparing an inventory that will be published soon on that all these data are quite scattered, they are not harmonized, and it's a pity because they have a huge potential that is basically demonstrated in the toolbox. So what would be capable to do if all these data would be harmonized and a good resolution? Second, we try to adapt the tools and maps in the Sprint toolbox to identify and target pesticides and cropping combinations that really would pose the highest risk for human and environmental health. And we based these models for the pesticide usage data. So we actually demonstrate what we can really do with this data, how we can prioritize in space and time, and how we can target the measures. And finally, that we would like to propose some different indicators than is just hazard risk indicator 1, which is currently used in Europe, with some annual indicators that will really account for the real pesticide usage. For example, our annual maps from the Sprint toolbox can be more resolute and also spatially explicit, and perhaps better for the assessing of the success with our transformation to the more sustainable pesticide use. Thank you for your attention.
Thank you, Jakob. I'm looking for a question, not from somebody in Sprint, who's had 5 years. So somebody in the audience who's not from Sprint, if you have any question, this is your moment. Okay, just right. No, okay, that's perfect. We've had that opportunity. So I'd really like to invite up to the stage Farshad, who's here. Sorry? And then I was going to say Claudia and oh.
Yes. So Jakob, there is a question online. And it says, it looks like the GenApp assumes if a pesticide is available, it will be used to the maximum level possible. It would be a very conservative approach. Farmers and their advisors make decisions to use pesticides based on levels of pests, weeds, and disease, not just apply them because of the product label says they can. And do this to the maximum allowed level.
Yeah. So actually, this is quite a detailed question. Yeah, somebody perhaps understanding very well the data. Yeah, of course, we were working with this, let's say, good agriculture practice application rates, which is really conservative approach. But we finally decided to also base our estimations on the real usage. So the data that farmers report, how much they consumed in each area. And finally, we basically coupled these two data together. So we can also validate the estimates based on the usage with this good agriculture practice. So if we had a higher input rates, then we can see it and we can tune and cut the application rate according to the application recommended application rate from the registration dossiers.
Thank you, Jakob. Just to say thank you very much for that and the toolbox, and there will be more updates on the toolbox coming forward. So please come to the Sprint website, sign up for all of the Sprint socials and newsletter. So now we're going to take a turn to the farm, and we're going to have discussions about cost-benefit analysis on the farm. We have some colleagues who are in Fiebel who are going to join us online, and Farshad is here in person. So I think in the running order, we have Claudia from Fiebel first. So Farshad and I will grab a seat for a moment.
Okay, thanks a lot for the introduction. So I hope you can all hear me. I'm also sorry for not being present. I have the pleasure to present the results from the cost-benefit analysis in Sprint. This work was shared by Fiebel, the Research Institute of Organic Agriculture, and DTU, the Technical University of Denmark. And our objective was basically to evaluate current crop protection practices at farm level with respect to environmental and economic sustainability, and also to evaluate strategies to reduce the reliance on synthetic pesticides. And for this, we used many different data sources. So we used data from the Sprint case study site farms. We used pesticide application data from an industry partner. We used FADN data, so data from the farm accountancy data network. And we also conducted expert interviews and used qualitative data. So this is the outline of the presentation today. So we basically looked at the status quo, what are current crop protection practices, and coming out from that, what are opportunities for reduction, what are strategies to reduce the reliance on synthetic pesticides. And we looked at private costs of current crop protection practices. So we specifically compared organic and non-organic farms, but we also looked at the external or societal costs of current crop protection practices. So also for non-organic and organic farms. And then we looked at specific intervention strategies that reduce the reliance on synthetic pesticides. And we looked at their perceived economic viability at farm level, and also the potential to save costs at societal level. And at the end also of this presentation, I will summarize our results in the form of policy recommendations. So let's first look at the status quo, namely the current crop protection practices and opportunities for change. This work was done by Jennifer Mark from the Research Institute of Organic Agriculture, who is also online today with us. So basically, she gathered data from the Sprint case study sites, agronomic data. And so in each case study site, there were around 10 to 15 farms. So the samples cannot be considered representative, but the data is very detailed. So we collected very detailed agronomic data related to crop protection. And these farms were usually organic, but also non-organic farms, so covering different management systems. And this data is stored in an Access database, which is publicly available. And Jennifer also published a paper containing the analysis of this data. And I would like to show you some highlights of this data analysis. So one important result was that pesticide dosage applied during cropping season varied up to a factor of 20 around recommended doses. So here, certainly, advisory would be a good instrument to support farms in sticking to recommended doses. Then another few highlights are that perennial crops have the highest expenses and interventions for pesticide use. The substances which are by far the most important pesticides used in terms of frequency of use and quantities applied are sulfur and copper. And then we also detected some active substances that are applied that are not renewed or that are actually candidates for substitution. And this state-of-the-art collection of data really helped us to identify pesticide use reduction strategies for this cost-benefit analysis. And in terms of opportunities, there is different opportunities which were identified to reduce the reliance on synthetic pesticides. For instance, the use of resistant varieties, wider crop rotations, replacing synthetic plant protection products by organic plant protection products, and also stronger advisory support. So please refer to the published article. Then we also looked, my colleague Johan Blokkel, also from the Research Institute of Organic Agriculture, he did an econometric analysis to compare the farm level costs of organic and non-organic farms. He used FADN data for that, so farm accountancy data, network data, which is a very large data set and covers a large variety of cropping and management systems. And his main goal was basically to quantify the economic effect or impact of adopting organic farming. And it is important to say that here, when he looked at costs, he only looked at the variable costs, so not at the fixed costs, for example, for machinery equipment. And here you can see some of the results. So he found basically that adopting organic farming leads to relevant cost savings related to crop protection and fertilization, and also for crop-specific production costs overall, and that holds for all farming types. And he also found that there can be cost saving related to labor, even if only minimal. But it is important to point out that subsidies still play a fundamental role due to differences in yield gap and also the certification, differences in yield. So because of the yield gap between organic and non-organic, and also, of course, because of the certification costs. So the publication is also out soon. So if you are interested in further results, get in contact with Johan Blokkel. He is also online today if you have further questions. And now I would like to hand over to Farshad, who is with you in the room.
Thank you, Claudia. Okay.
Just tell me next slide when I have to change the slide.
Claudia, you have control on the slides?
Yes, I'm in control of the slides. Yes.
Okay, perfect. Hello, everyone. I'm Farshad from DTU, Technical University of Denmark. Now I'm going to present works done in tasks 6.1 and 6.2 on environmental sustainability assessment of different pest control scenarios. Actually, we will give you a broader picture of sustainability assessment. So actually, we quantified impacts and damage costs of different pest control scenarios, and at both level, farm and regional. For farm level analysis, we actually applied life cycle assessment approach, considering whole life cycle of all inputs involved, including supply chain impacts and on-field impacts of all inputs involved, including pesticide, agricultural machinery, and diesel fuel consumed in agricultural machinery. The importance of farm level is related to having an analysis on possible trades-off between different aspects. For example, during a transition to more sustainable approach on pest control. For example, for toxicity versus land use and climate change, etc. We have a special focus on pesticide use impacts on farm. Also, we did analysis on regional level. Actually, we quantified concentration and impacts at regional level using ANGIA multimedia environmental fate model, which we developed and refined for this purpose. Yes, the importance of the regional level analysis is important for policymakers mainly, to have targeted intervention, policy intervention, evaluation and monitoring, risk prioritization, and strategic planning. Next slide, please. Okay. Before going to next slide, we have a special, as I said, we have a special focus on pesticide use impacts as the main core of this analysis. For this, we connected three aspects: pesticide use on farm, pesticide emissions, and pesticide impacts. Then finally, we translated all impacts to damage costs. Here you can see a brief of farm level results showing the contribution of each input to the total impacts per considered area of protection: human health, ecosystem quality, and mineral resources. For actually, you can see we separated input impacts based on their supply chain impacts and on-field impacts, which differentiated with different colors. As you can see, pesticide-related impacts are dominant in all area of protection, with contribution of around 95% in human health, 70% in ecosystem health, and 60% in mineral resources in conventional and IPM. Another result that we observed high impacts in some IPM and organic farming, which is mainly driven by fungicide, copper-based fungicides. So considering the importance of pesticide-related impacts, we upscaled the impacts to regional level. Can you change the slide? Okay, here you can see the regional level human toxicity impacts across considered countries. We expressed the impact score based on the Delhi Disability Adjusted Life Year. And as you can see from the results, total pesticide use impacts across all crops in considered countries was obtained around 300,000 Delhi per year, which means 21 human day lost per year. for each EU resident. If we consider whole lifetime, it can be equal to 3 to 5 years of last. And we found 5 pesticides as main contributor to the total human toxicity impacts, as you can see here. And among the spring crops considered in spring, grapes and apple had highest human toxicity impacts. Now we will go to next slide. Yes, here you can see the regional level ecotoxicity impacts, which expressed based on a species lost over a year over considered area. And we quantified a species lost in freshwater and soil terrestrial ecosystem. As you can see here, France and Spain showed highest impact, highest ecotoxicity impacts. But when we consider the area-specific impact, agricultural area-specific impacts, we can see Portugal and Switzerland with highest impacts. And 3 pesticides were identified as main contributor. Also among the crops, maize and grape had highest ecotoxicity impacts. Next slide, please. Finally, we translated all impacts to the damage costs, the monetary value, which is also known as external cost, which is different from typical costs. The cost that imposed on society, costs that society should pay for compensating damage on human health and ecosystem. So, as you can see from the results, the total damage costs across all crops in considered areas, countries, was obtained around 23 billion euro per year, which mainly was related to human health impacts. Italy and France showed highest impacts, but for providing more sensible indicator to show the intensity of external costs, we compared damage cost versus agricultural GDP in each country, which was in range of less than 5% for Netherlands and Switzerland, which is good, almost, and around 40% in Slovenia and France, which is not, I think it's terrible. So, yeah. And I also highlighted here the main contributor to this high damage cost. As you can see, terbutylazine in both France and Slovenia, along with tebuconazole and methyram fungicides in France. Yes. Also, for last thing, I know my time is limited. We provided inputs for also for toolbox. I didn't have time to show the concentration maps, and also our data were used for defining a reduction strategy. Yes, that was all from my side.
Okay, thanks a lot, Farshad. Here you can also see the publications that comes out of this work. Then, as I said, we also looked at intervention strategies and the perceived economic viability at farm level of these intervention strategies. And we talked to experts from sprint case study sites. And we did this for 4 case study sites. So we looked at silage maize, vineyards, apples, and seed potatoes. And we looked at intervention strategies like product substitution, mechanical weeding, intensification, wider crop rotations, robust varieties, a low residue strategy where only organic plant protection products are used after flowering. We looked at foil coverage and also organic production as intervention strategies and evaluated these where applicable in these case studies. And here I just would like to point out some of the highlights that we found in these interviews. So product substitution is a cost-effective way for conventional or IPM arable farms to reduce their environmental and health impacts, but the implementation certainly needs to be accompanied by appropriate policy regulations and financial incentives. then mechanical weeding only was also perceived as an economically viable option for these farms. But they need access to appropriate machinery and technical assistance. So fixed costs could be an issue there. Then disease-resistant varieties were also perceived as a cost-effective way for conventional and IPM orchards and vineyards. But a big problem is the market demand and also the AOC regulations, so the control designation of origin specifications. They must be relaxed to increase the use of resistant varieties. And the low residue strategy was also perceived as an economically viable option for conventional IPM orchards, but there also financial incentives are needed, and especially the handling of storage diseases was an issue in terms of also equipment needed to handle storage diseases properly. And generally, it can be said that farming without synthetic pesticides is perceived as very risky by IPM and conventional farms. Thus, reducing the reliance on synthetic pesticides also implies reducing farms' perceived production risk. It's the word perceived is very important. Then generally, to reduce the reliance on synthetic pesticides and also this perceived production risk, farms need access to effective machinery, they need technical assistance, they need financial support, and they need effective non-synthetic product alternatives. And to reduce the reliance on synthetic pesticides, the demand for disease-resistant varieties and low-residue pesticide-free and organic products needs to be really strengthened. Okay, and now I would like to hand over to my colleague Adrian Müller, who will speak about the potential to save costs at societal level.
Yes, hello, thank you. I'm Adrian Müller, also from FIBL. And our question in this task was to investigate what happens if these pesticide reduction strategies are upscaled to a regional or national or like whole EU level, so hundreds or thousands of hectares. And how we did this was basically to assume that we implement the strategies on 1,000 hectares, sort of as a comparison area. And we assumed that in the baseline, we have the baseline farms to equal shares from the case studies we looked at, cropping these 1,000 areas, and in the scenarios to have the farms implementing the reduction strategies, cropping these areas. This is old because we couldn't work like with representative samples of pesticide reduction strategies. This could be scaled up as representative for the whole of EU or for the whole of certain countries. So we use this approach to illustrate what happens if we scale this up. And the key result we get from this is detailed information on how the cropping patterns, the yields, and food and feed production and pesticide use and related impacts change. And especially what we are interested in, what happens on food system level. So what happens to the total food production if we scale up these strategies? That's basically the question behind, and that's why we need a food system model capturing all these flows after harvest, basically. Next slide, please. So we implemented it in 3 case studies. You already saw this in the earlier slides. Details are in the deliverable 6.5. And it is sort of a combination of different strategies to various extents, also with some interaction with changes in rainfall intensity, because it was highlighted that this may influence the yields under different reduction strategies like mechanic weeding. Next slide. And in more detail, we looked at like robust varieties, which resulted in different yields and input use, the low residue strategies, also with different yield and input use and an interaction with rainfall intensity. Then we had certain agroecological practices where very important is a wider crop rotation. So the key crop is less frequent in the crop rotation, and you have different crops. So you have a different production pattern, similar for the organic shares. The mechanical weeding, also with the interaction with rainfall intensity that may affect the yields. And so these sort of practices were then put to the model and scaled up to see what happens. And the basic mechanics that drives results is that different yields, clearly, or lower yields, for example, for organic, clearly result in changed or reduced production quantities. Different input use results in changed pesticide use and related environmental impacts, and different crops from different crop rotations, for example, results in different production patterns, and especially maybe less production of a key crop for food or feed and more production of other crops. So could also be more like forage crops, grass clover lays into crop rotation. And a very short illustration of results. So what you can expect here is if we adopt the agroecological practices in the case of Netherlands and organic management, with increased shares of this area cropped with these reduction strategies, the costs go down, as one would expect. And this is a little bit biased because we had only the costs from these three impact categories for the key crop, not for the alternative crops that were added there. And to the right, you see how the food and feed production changes relative to the baseline. And this is measured in just feed energy provided. So we didn't make at this stage assumptions on how this feed would be fed to which type of animals and so on, because this would further blur the results. It's just to illustrate how drastic changes may arise regarding food reduction and feed increase, in this case of the seed potatoes in the Netherlands. For more details, I refer to the deliverable. And finally, what we draw as some big discussion points. So clearly the reduction strategies contribute to a reduction of the damages along all these three key groups of costs we had from the overwork tasks. They tend to lead to reduced production, but combined with other strategies such as reduced feed production from croplands or food waste and loss of reduction, these reductions in food production or food supply could be counteracted. And this is the key thing, that implementing pesticide reduction strategies, which was basically a production decision without thinking about the whole food system consequences, which links down to the consumption patterns, is not the holistic way. So one should always think about the production and consumption patterns together when implementing such pesticide reduction strategies at large scale. That's what comes out from this upscaling, basically. And shortly, this caveat again, we didn't have all damage costs for all the crops included in the simulations. Then I hand over for the policy recommendations to Claudia.
Okay, thanks a lot, Adrian. So just to summarize some policy recommendations for you. So the pesticide reduction strategies are that we looked at are economically viable very often, but farmers need to be compensated for reducing societal costs. And if their perceived risk of implementation is needs to be addressed through effective advisory support and also information and awareness raising measures. Then very important also, what just was also pointed out by my colleague Adrian, pesticide reduction strategies can change the production basket and thus food and feed supply considerably. So if these strategies want to be upscaled, a whole food system perspective needs to be adopted. So for consistent implementation, action on other aspects such as dietary patterns and food waste and loss should complement pesticide reduction strategies. And here, some policy recommendations mainly coming from my colleague Farshad. So one recommendation is that data sharing protocols between farmers, researchers, and policymakers need to be strengthened to enhance real-time tracking of pesticide impacts. An EU-wide monitoring system needs to be established that uses advanced emission and impact models to guide pesticide authorization decisions. Then we need to support knowledge sharing platforms to help farmers transition to lower impact pest control methods, aligning with the COP's emphasis on sustainability. And we need to strengthen policies around monitoring and enforcement to ensure compliance with EU-wide regulations and transition targets. So this is our last slide. Thanks a lot for your attention. And please, we are open for questions.
Lovely. Thank you, Claudia. Thank you, Adrian. And thank you, Farshad. So we have time for one quick question. I'm just looking out to see if anybody... Oh, the gentleman there waved his hand. No. You're next. Okay. You're keen to get on. Yeah. Please.
I have a question from Chris. Is it appropriate to present the total damage cost without presenting any value for the societal benefits of pesticide use?
Yeah, you're right. But we aimed here just to show the damage costs, not focusing on, yeah, you're right. For having a final conclusion, also we need to consider the benefits, which I think somehow reflected in by Feeble and Adrian, I think. But yeah, you're right. It's not for final conclusion, but it's a warning that we need to consider how big can be damage costs. It's kind of it's warning, not for final conclusion.
Great. Thank you very much. Thank you very much for Chris. I'm wondering if that's a different Chris from the last online question, or is the same Chris. So thank you, Farshad. Thank you, Claudia.
There is a
and
comment
thank you,
from
Adrian. That was
Adrian.
great. Thank you.
There is also a comment from Adrian.
All the way through this project, we have been mentioning that we've been working with other people, including farmers. And as I think it was probably Peter's, keen to get on stage. So please do come up. And Francisco as well, please. And I think Lindsey is translating for Francisco. So come on up, you three, please. It would be great. So it's good. What a time to meet just before you get on stage. Take a seat. Shall we start with Peter? Yeah, please. Do you have slides or you talk? Okay, yeah.
I should use a little bit the pedestal to use. Dear ladies and gentlemen, my name is Peter Apat. You have probably never heard from me, which is nothing uncommon. I'm coming from a medium farm in Slovenia, where we don't have an extraordinary big herd of cattle, or in any case, we don't have an extraordinary big tractor, or even don't have an extraordinary big debt to a bank. But I was nevertheless asked to present the extraordinary story behind the Zavod Ceneno, Slovenian hay initiative and hay-based production of milk and meat in Slovenia. Based on our farm story, I will try to point out how, on one hand, hay-based production can be focused on the reduced use of mineral fertilizers and pesticides, and on the other has the impact on a higher farm income. Okay. On our farm, we are working on approximately 20 hectares of farmland and 20 hectares of woods on mostly hilly terrain. Our cattle herd had approximately 20 milking cows, 15 heads of young cattle, and a couple of pigs. As many other farms, we were oriented in conventional milk production. Until the year 2019, we produced approximately 100,000 liters of milk per year. And on our fields, we have grown approximately 5 hectares of maize for silage. Other fields grown grass, which we harvested, first half as a grass silage and other half as a hay. Because because the maize need a lot of nutrition and protection, we use quite mineral fertilizers and pesticides. In period 2015 to 2018, on our farm we used 37 tons of mineral fertilizers, 90 tons of grains for cattle feed, and 38 liters of pesticides like herbicide, cambio, and Mustang. And then why we decided to go to transition to the hay production. There is a big lack of farmland in our valley because of the coal mining. In 150 years of mining history in our valley, we lost more than 300 hectares of farmland, and we are still losing it. So there weren't and are still no possibility to expand our farm locally, which forced our family to adopt somehow. First steps were made by my parents in 1994, when we started our touristic farm, a farm-based restaurant for pre-appointed groups. In 2008, we also added a country house stay with the 4 apartments for rent. And because there is no touristic farm without a farm, we are starting to think how to gain more with the same or even less also in our barn. Our local dairy factory started with the hay cheese test production and looking for a hay milk suppliers. As a farm that was already a quarter in a hay-based production, we decided to take a hay way and add a value to our base product. The transition was not easy, not even cheap. And how the transition was made? We had to upgrade our farm with modern hay drying system for loose hay and round bales, a hay crane for manipulation, a hot air system based on 150 kilowatts biomass furnace and a 40 kilowatts of solar panels. With this, we also reduce our dependence on the outsourced energy and become more CO2 neutral. Complete investment was approximately around 200,000 euros, and it was supported in 50% with EU subsidies for generation transition and upgrading farms. The transition took more than 3 years, but on the 10th of February 2019, we officially become a first hay milk producer in our valley. Okay. After that, we never turned back. Luckily, we kept most of our farmland, or at least we could replace it locally. We use 2 to 5 hectares on the steepest and closest meadows for a pasture. On the rest of the 15 hectares, we harvest hay and fresh grass for feeding our cattle. Besides 15 hay milk production cows, we now raise also Angus and Wagyu suckling cows for top quality hay-fed beef steak production. With the same size of herd, we produce approximately 80,000 liters of milk and 40 kilos of hay-fed top-end steaks. In the period 2021 to 2024, on our farm usage comparing to the period before, we reduced for 50% less of mineral fertilizers, for 20% less of grains for cattle feeding, and for 90% less of pesticides, because now we only use it for some point-to-point spraying for weeds on our grass fields. Economic and social aspect of hay-based production. Our customers instantly noticed the difference. There was less smell in the barn and around it. More locals start to buy fresh milk at our farm. A lot of time saying that the taste of the milk is the same like it has it when their old parents still have a cows. Local pastry shop noticed the huge difference in milk quality for making cakes, sweets, and ice creams. The price of the hay milk sold to the dairy factory is higher for 7 euro cents, So the income from the milk is approximately 20% higher than from the if you go stay with conventional milk. Price of the milk we sold on the farm is 1.2 euro per liter, which is 50% more than conventional milk. And also customers have found out that the hay-fed meat has better taste than grain-fed one and are willing to pay up to 50% more for it. We are selling Angus Wagyu mixed steak packages for 40 euros per kilo. So now a little bit or some words about Zavod Ceneno Slovenian Hay Initiative. Zavod Ceneno or Hay Initiative, it was founded by 8 farmers and 1 dairy factory in 2020 during the European Innovation Project, Hay, Meat and Milk. Membership is not mandatory, and that is why our current number of partners is 26. During this project, we organized also that the EU TSG, this is traditional specialty guaranteed, hay milk specification to also become valid in Slovenia. Our hay initiative with the partners was the main initiator to include hay production as one of the environmental climate measures in the Slovenian Rural Development Program for period of 2023 to 2027. All these actions led from 42 hay farms in 2022, with altogether approximately 1,000 hectares of farmland, to now, so the data was from 2024, 879 farms with more than 16,600 hectares included in hay production. This means expansion from 0.2% to around 3.8% of all farmland in Slovenia. One of our biggest success was also preparation of the hay-fed meat specification and organizing to file it on the EU Commission, which led to now EU TSG valid specification. Because it's not smart to rest on your trophies, we keep on moving the wheel. In cooperation with Šaleška Dolina Agricultural Cooperative, we managed to organize the first bio-hay beef cattle buyback program with additional pay of plus 10% for hay-raised cattle. So, I know I'm quick, but I have to end it a little bit. And for the end, also my message to the decision makers all around Europe. First, what is the definition of farmers? For a lot of people, is like this. Those are the people who are responsible for slurry smell on the sunny days, for noise on the weekends, dirt and crowd on the roads during the picnic and holiday season. And there is a many variation of us. From a small farms with only couple of sheep and chickens, fruit or vegetables farm with less than 1 hectare of fields, to mountain farmers that harvest hay on the slopes that many of us could not even stand on. Farmers that must have a job to work, and to keep farming. And also to big corporation with thousands of hectares of fields, a couple of thousands of cows and hundreds of employees. Yes, it's true. We are all feeding the world. But small farmers, we produce food for ourselves and sell what we have extra. We know all the animals by their names. We cry and curse when the hailstorm destroys our corpse. Or when it happens that one of our animals dies. We also work and help each other to make our life easier. But big corporations, they are run by managers who don't care what and how they produce. They care only for growth and profits. So, do you care for what do you want to have on your plates tomorrow? Support small farmers. It's true, small farmers, we are not the most sophisticated people, but we are more than care for what we produce. So just let us do what we like the most, and we promise we will make miracles out of it. And we will be able to put all these miracles on your table. So let's make together an invigorating environment where the future generations will embrace tradition, knowledge, and hard-working habits needed for quality and local food production. Thank you. This is all from my side. So if there is any question, I will be glad to answer you. Thank you.
Thank you, Peter, and thank you to Peter's family by the looks of it as well, which is lovely to see. Are you staying there, or do you want to come over here? Lindsey, Francisco? Oh, no, you stay there for a moment.
This one, yeah. Yeah, so I will. Es así, que avanzas. Sigues avanzando, sí. A ver. Y pues, please, pero just sit.
Buenas tardes a todos. Muchas gracias por la invitación. Soy Francisco Torró, soy ingeniero técnico agrícola y trabajo en la cooperativa Surinver de Pilar de la Horadada del sur de Alicante. Soy especialista en biocontrol, que es la técnica de control integrado que mediante el uso de organismos vivos conseguimos controlar plagas reduciendo los pesticidas.
Yeah, Francisco is joining us from the region of Murcia in the south of Spain. He's a representative of the Surinver group and a specialist in biocontrol, the use of living organisms to control pests.
Trabajo en la zona geográfica del campo de Cartagena, está en el sureste de España, y es una zona donde conviven 1.800 hectáreas de cultivo de invernadero, mayoritariamente en monocultivo de pimiento, y conviven con cultivos de aire libre y cítricos.
Yeah, you can read the data on the slide, of course, but this is a region with lots of intercropping of greenhouses and arable outdoor crops in the region of Cartagena, mostly peppers and citrus crops.
Yo empiezo a trabajar en el año 1993 y me encuentro una situación fitosanitaria desesperada. Thrips franquiniella occidentalis estaba en una situación incontrolable químicamente, transmitía el virus del bronceado del tomate y la incidencia en los invernaderos era muy alta de este virus. Había un interés muy alto ya en los consumidores por incrementar el tema de seguridad alimentaria en aquel momento.
Yeah, so the starting conditions for this change was really a desperate situation and a crisis where these greenhouses had a high incidence of this tomato spotted wilt virus. As you can see, the chemical control was no longer effective, and at the same time, there was increased consumer demand for quality and safe food.
Cuando empiezo a trabajar, pues lo primero que hago es observar qué era lo que estaba sucediendo. Nos dimos cuenta que al final de cultivo, cuando los agricultores dejaban de tratar químicamente, las poblaciones de trips se estabilizaban y había una entrada natural de depredadores. Al mismo tiempo empezaron a aparecer las primeras explotaciones ecológicas que tenían, curiosamente, mejor resultado que donde se estaba aplicando químicos. Y la situación era en aquel momento desesperada y los agricultores pedían un cambio en la técnica.
Yeah, again, in this desperate situation, the starting conditions were observations. So seeing that when, at the end of cultivation, when chemical treatments stopped, so when the less use of insecticides, is exactly when you saw natural predators enter the greenhouses and actually better control the disease and the thrips than through chemical treatment. And the farmers were influenced by the desperate situation and also the beginning of organic cultivation.
Lo primero que hicimos pues, era observar el entorno y nos dimos cuenta que en la flora espontánea había un montón de depredadores. Empezamos dejando de tratar los invernaderos con productos químicos, promoviendo la entrada de depredadores naturales. Incluso cogíamos flores donde habían depredadores y los introducíamos en los invernaderos. Pero estos primeros ensayos no fueron suficientes, el trips estaba muy infectivo, la situación fitosanitaria era muy grave y había una alta incidencia de virus. No conseguimos nada con esto.
Yeah, as a first attempt, we actually started from the wild environment, so observing the natural predators and of the thrips in natural environment, even bringing in local plants where these thrips were, the predators of the thrips were living. and doing everything they could to promote the natural entry of the predators, but it didn't work initially. What they realized was that there were, actually, go ahead. Yeah.
En el año 1994-95 empiezan a aparecer los primeros insectarios profesionales y empezamos con un invernadero de solo 2.000 metros soltando depredadores Orius y Amblyseius cucumeris. Tuvimos un excepcional control de trips y la incidencia de virus fue mejor que en el testigo químico. Los siguientes años empezaron a aparecer más insectarios, pero el segundo año no fue el éxito tan grande. Teníamos 3 invernaderos y 2 de ellos acabaron muy mal. El tercero era ecológico y iba mejor. El establecimiento de los depredadores no fue muy bueno en estos invernaderos. Lo que sospechábamos que había algún problema de residuos. Los siguientes años la evolución fue lenta por eso, porque persistían estos problemas de instalación de auxiliares y no sabíamos exactamente por qué.
So the big change happened in the first year when they started working with professional insectaries and introducing insects bred for biocontrol. And with this greenhouse space of 2,200 meters, had really a lot of success, really good control of thrips, better than they'd seen with chemical control over many years of trying. By the second year, they expanded the operation to other greenhouses, and actually they got very poor establishment of the predators of thrifts, the biocontrol insects, and except for one organic greenhouse. And that led them to suspect that maybe pesticide residues in the traditional farms, even if they weren't spraying actively at that time, were influencing the predators. So the predator insects were being impacted by the residues.
Los siguientes años empezamos a poner hipótesis por qué esa escasa instalación de Orius y siempre encontrábamos algún motivo de residuos. Estábamos usando quizá insecticidas aparentemente compatibles que no lo eran. También los agricultores pues, podían tener residuos en las cubas de tratamiento. Total, estuvimos 5 años estudiando cuál era el problema. Al final nos dimos cuenta que el problema era un residuo de una aplicación que hacíamos antes de trasplantar el pimiento para desinfectar la estructura y nos estaba hipotecando la evolución de los depredadores durante toda la campaña. Cuando conseguimos determinar esto y eliminar ese tratamiento, rápidamente ya pasamos al 100% de nuestra superficie en la cooperativa. En el año 2001-2002, el 100% de nuestra superficie estaba en control biológico.
So then they went through several years of trying to uncover what the problem was, what was the residue that was preventing the establishment of these natural predators. And there were pesticides that were supposed to be compatible, but they weren't. There was also residues maybe in the buckets or other kinds of instruments they were using to treat. But eventually what they finally figured out was that it was a treatment that was being applied in the greenhouses before they even planted the peppers. And by the time once they figured that out and eliminated that specific treatment, then everything went really, really well, and they were able to go to 100% of their area using biocontrol.
Bueno, en las barreras que nos encontramos para conseguir hacer avanzar el sistema, pues era el control de otras plagas, además de la principal del TRIPS. Existían plagas como conocidas ya, como la mosca blanca, los pulgones o las arañas rojas, para los que hubo que buscar soluciones. Unas fueron biológicas, otras tuvimos que buscar insecticidas químicos que fueran compatibles con la lucha biológica.
Yeah, of course, there are other pests that they already knew of and had to look for solutions to introduce biocontrol, but also where chemicals were needed to make sure they were not working against the biocontrol mechanisms they had in place.
Al mismo tiempo nos aparecieron plagas que la gente no conocía porque en los invernaderos químicos, al usar insecticidas de amplio espectro, no aparecían esas plagas, aunque no se estaba tratando directamente con ellas, como por ejemplo por los chinches o las cochinillas.
Yeah, then of course when you take away the broad spectrum insecticides, maybe pests you aren't used to dealing with appear, so it's time for new solutions.
El siguiente problema era la formación de los agricultores y de los técnicos. No había conocimientos suficientes y tuvimos que hacer una amplia un esfuerzo muy grande. Estuvimos 4 o 5 años haciendo cursos en la cooperativa, buscando los mejores expertos y haciendo un curso muy práctico que ha perdurado hasta la fecha. Los agricultores siguen conociendo los insectos, hablando técnicamente de nombres científicos y los conocen perfectamente.
Yeah, they basically had to, let's say, create a bespoke training solution to pass on this knowledge, which meant calling in the experts from the insectaries and really creating a technical knowledge base. And so their farmers are really, really well informed. They know all the Latin names of the insects and see themselves as being able to pass on this knowledge as well.
La siguiente barrera era la económica. Había poca oferta de depredadores, se necesitaban altas dosis de sueltas porque el problema era muy grave y se añadió el coste de la necesidad del control técnico, que no era común en aquella época. Entonces eso incrementaba el coste, pero al final el beneficio era porque el resultado era bueno, el control era bueno.
Because of the need to release lots of insects, it was actually more expensive to do it this way than to treat with chemicals, but it was easily accepted by the community because it was working.
Y bueno, ¿cómo conseguimos superar estas barreras? Pues tuvimos el agricultor estaba por la labor de buscar una solución. Tuvimos el apoyo de las instituciones públicas, universidades y centros de investigación, y los investigadores nos provinieron de los conocimientos suficientes para poder desarrollar el sistema. Gracias al acuerdo de todas las partes implicadas, pues ese dato de 2007 está obsoleto. En 2007 habían 10.000 hectáreas de cultivos protegidos en el sureste español con control biológico. En el 2022, solo en Almería habían más de 25.000. Yo creo que habrá más de 30.000 hectáreas ya en control biológico en España.
Yeah, a big factor in overcoming these barriers, you can see these 3 factors here. So the agreement of practitioners, institutions, and researchers. I won't read that. But one point is here, we're talking about 10,000 acres in 2007. That's grown substantially, and also to the neighboring region of Almería, which is an important agricultural region and also has these greenhouses. So it's, I think years ago you said it was 25,000, it must be even more now.
Bueno, el desarrollo que tuvimos, pues fuimos incorporando nuevos elementos en el control biológico, nuevos insectos para controlar otras plagas y poco a poco hemos introducido un montón de insectos.
So new aids and biocontrol for new pests.
Y otro cambio que hemos necesitado, pues esta es la situación de partida de la mayor parte de los invernaderos en la zona, una simplicidad ecológica muy grande, monocultivo, erosión, desarrollo de plantas adventicias que a veces nos pueden generar problemas de virus. Al final necesitábamos revegetar la zona, fomentar la biodiversidad, instalando setos y promoviendo la biodiversidad.
Yeah, we can see that they took the transition outside the greenhouses as well because of these monoculture, very simplistic scenes, and the opportunistic plants that were rising up in this situation were creating more virus opportunities. So they've done a lot of installation of hedges and biodiversity measures.
Y lo que hemos hecho pues, ha sido aumentar la biodiversidad funcional dentro de los invernaderos, poniendo especies vegetales que favorezcan el desarrollo de los depredadores, incluso manejando las malas hierbas a nuestro interés. Y este es el resultado dentro de los invernaderos.
And biodiversity within the greenhouses, which you mentioned earlier is also sometimes hard for farmers to accept because they have to give up a little bit of the cultivation space, but the benefits are there.
Y en el exterior pues también hemos actuado revegetando la zona con vegetación autóctona y este es el resultado. El cambio es evidente y el beneficio ecológico inmediato.
And biodiversity around the greenhouse also with good results.
Y bueno, los resultados pues destacar sobre todo el beneficio económico derivado de la efectividad del sistema. El sistema funciona, el sistema permite un control eficaz de las plagas y eso implica el beneficio económico. Y el beneficio en el ecosistema ha ido más allá de los invernaderos de pimiento. El ecosistema agrícola de la zona ha mejorado en general, todos los cultivos al aire libre han mejorado, porque ya de dentro de los invernaderos no sale nada negativo, sale algo positivo, aunque solo se haga biocontrol en los invernaderos.
All right, so you can see the list of results here, and I won't read every one, but we really want to point out that there's an economic benefit, even though it costs more. Just the fact that this was effective made it economically viable and seen that way by farmers. And then also, unexpectedly, perhaps, in the fields outside of the greenhouses, even though they weren't using biocontrol, they saw a lot of benefits because the viruses weren't traveling as often from the greenhouses to the outdoor area. So that was a secondary benefit for other members of the farming community.
Y bueno, y los retos del presente, pues una de las cosas que ha estado ocurriendo es que está aumentando el cultivo ecológico, con lo cual necesitamos implementar más control biológico en el sistema. La eliminación de materias activas también nos induce a aumentar el control biológico. Hay como problema una cierta relajación en los agricultores en los últimos años, debido sobre todo a introducción de nuevas plagas, y a veces se reacciona con la primera opción, que es volver a la química. Y ese es un peligro. El cambio climático también nos está afectando, aumentando la agresividad de las plagas y el periodo en el que están atacando, y la introducción de nuevas plagas pues es un problema continuo. Y afortunadamente, por ejemplo, con Tripardispinus se demuestra que el control biológico sigue siendo la mejor opción, la única, diría yo.
Yeah, so challenges and topics for the present, of course, rise of organic farming means looking for new specific tools and types of biopesticides, et cetera. And there's still a tendency of relaxation, let's say backsliding from the farmers, where the new pest comes in and their first instinct is to throw a chemical for pesticide in, but then it kind of undoes the progress with the biocontrol. But even so, when they still see that biocontrol is effectively helping with emergent pests due to climate change and other problems. So.
Y solo enfatizar la necesidad, el sistema es frágil y necesitamos el apoyo continuo, necesitamos que se siga investigando en el tema, que las administraciones se impliquen y apoyen, porque ante nuevos retos como el cambio climático y la introducción de nuevas plagas necesitamos implementar más el control biológico.
Yeah, and even though this is working, the system is fragile. There's always emerging pests, and we have to continue researching, supporting research into this, the development of new methods and insects, and of course, administration and institutions that support that.
Bueno, gracias por su atención.
Great. Hold on one moment, Paco. Hold on. One moment, please.
Bueno, un aplauso.
Thank you. And I was just really hoping you were going to speak Slovenian then. That it'd been like a secret you've been holding all these years. Thank you very much. And thank you to our farmers. For many of the researchers in the team, of course, we couldn't do any of this research without farmers, and they are our constant companion in our research and in our work. So it's lovely to be able to welcome them to an event like this with their friends and family as well, which is really lovely. We are going to give you a 10-minute break now, and we will be sharp about the 10-minute break. So do whatever you need to do in 10 minutes flat and be back. Okay, thank you. That's better. Okay, we are going to start again. We are in the last lap of our day, which has been a very full day. Much excitement, much to learn, and I appreciate your patience and also your mental stamina of getting this far. So we have one presenter who's going to appear online. Then Antonia is going to join us for some policy recommendations, and we're going to have a panel. And then also excitingly, we're going to have the results of the poster competition. So not far to go now. So I'm going to get ready to hand over to Domenico, who I'm hoping is online. I'm just looking for a thumbs up online.
Yes, I'm here. I'm here, yes. Can you hear me?
Excellent. Thank you, Domenico. Lovely to hear you. And so we have 10 minutes from you. Thank you.
Thank you. Do I share the slide from my side, or because I saw on the screen you're just projecting something?
Slides from Domenico's side or our side? Our side. Okay.
Okay, equal for me. So I can maybe start with my presentation then. Good afternoon, everybody. I'm really sorry if I could have not been there today. My name is Domenico De Serio. I'm a policy officer at the European Commission, working in the unit dealing with access to market of pesticides, in particular biocontrol. Today I will describe you the biocontrol in the EU under the framework of Regulation 1107/2009, starting from our legal framework, describing the biocontrol in the EU and our initiative to make it easier to access to market, and future developments. Slide, please. To start with, just a short description of our legal framework, Regulation 1107/2009, based on access to market of pesticide. Placing pesticides on the market is basically foreseeing two steps to take a plant protection product to the market. First of all, the active substance approval that must occur at EU level. To take an active substance to the market, the applicant needs to submit a dossier for the active substance itself and a dossier containing one representative formulation used. If the active substance is approved, is on the market, then the applicant can seek authorization at member state level. You, of course, an applicant would need an authorization for every type of use in member states. Slide, please. To give you just an hint about how the flow works, in the example of active substance access to market, the application starts when an applicant, of course, submits a dossier to a rapporteur member state. The dossier is submitted according to implementing regulations called data requirements. So basically a list of data which are necessary to be included into the dossier. To be assessed, can you please click a couple of times because there are animations here? Thank you. Which dossier is submitted by the rapporteur member state. So here the risk assessment part starts. I see that in the chat someone is saying that the slides are not visible online. I can see them, so I just will go with the presentation, and then please, Chair, tell me what to do in case I need to act otherwise. So the rapporteur member states assess the dossier of the applicant according to other implementing regulations called the Uniform Principle for the Evaluation, and produce a report. This report of one rapporteur member state is then submitted to the European Food Safety Authority, EFSA, which steer a peer review risk assessment, which concludes with the production of the so-called EFSA conclusion. The EFSA conclusion is then handed over to risk managers, so us, that within the Standing Committee on Plant, Animal, Food and Feed take a decision on approval or non-approval of the active substance. Slide, please. In the EU, biocontrol substances are subject to more and more applications. We see here in this slide the total number of applications we receive. We see that more or less the application rate, it's fluctuating, but more or less remaining stable. But we see that the active substance submission concerning active substance which are not biocontrol is being reduced time by time, which is the light bar at the top of the chart. But this is very nicely compensated by the increased number of applications which concern biological pesticides. Slide, please. If we break down this data into the total number of active substances which are biocontrol and which are available in the EU year by year, we see clearly that the trend is increasing. So year by year, we have more and more active substances which are biocontrol increasing in the EU, among microorganisms, extract, pheromones, and so on and so forth. And we also see that the biggest part of the biocontrol active substances approved in the EU are represented by microorganisms, so which is the dark blue bar at the bottom of the slide. Slide, please. The good news is that microorganisms are most of the times approved as low-risk active substances, so they can benefit from a longer approval period, and they can be fully used in organic farming. So for this reason, we decided in our activities to foster access to market to biocontrol, we decided to give priority to microorganisms. We started in, as you can see, in 2020 with some guidance document, one on metabolite of concern, then 2021 on antimicrobial resistance. But the breakthrough was with the entry into force of new data requirements and uniform principles. I showed you before in the chart showing the time flow for the assessment of the dossier, where the data requirements and the uniform principle were part of the assessment criteria. They were adapted to new science and to the latest knowledge. Then in March 2023, we produced 2 commission communications, which are listing basically recommended test methods and guidance document to implement this new data requirement. Click, please. And in October 2023, another guidance document called explanatory notes, which further explain the new regulation that entered into force in 2022. We have ongoing other activities like the supporting at OECD level, so worldwide level, the development of new test methods and for microbial active substances in particular, because at the moment we are lacking many methods which are specifically designed for microorganisms. We're also working on systematic reviews. We are, well, the activity is almost concluded, but we are producing some collection from scientific literature to support future dossier preparation. And we are developing new guidance document, like we are amending a guidance document on active substances, which are viruses. A slide, please. Of course, we are not forgetting other biocontrol agents which are not microorganisms. So we have, for instance, pheromones or peptides, for an example. We, as regards pheromones, in 2024, in January, we amended a guidance document on semiochemicals. The amendment was basically expanding the scope of the already existing guidance document by embracing also other pheromones, which are not only SCLP, so straight chain Lepidoptera pheromone, but they were expanded to other types of pheromones, basically. And then there was another document called Problem Formulation, published still in January 2024, which is very useful, especially for those biological controlled substances, which are chemical by nature, for instance. I will tell you in a bit more details about this. We have an ongoing revision of also the data requirements, which concern data requirements part A, so the data requirement part that concerns chemical active substances, which of course includes also those chemical active substances which are also biological nature, like pheromone or peptides, as I just mentioned before. Slide, please. Of course, in the amendment of, the activities in facilitating access to market of biocontrol active substances, we encountered several challenges. For instance, we are basically taking initiatives, regulatory and non-regulatory initiatives on moving targets, because we have, like, for instance, new technologies coming on the market, like RNAi, peptides, and we need to have a legal framework which is flexible enough to embrace new technology coming to the market. I mentioned just before the problem formulation document, but also the regulation itself, the data requirements are allowing a dossier to be submitted even if the substance is a peptide, for instance, is an RNAi, so it's a very newly developed technology, because, for instance, data can be dismissed, waived, or adapted based on the nature of the active substance. Just to give an example, if you're talking about pheromones, most probably you would be able to waive data concerning persistence in the environment, because, of course, as we know, pheromones are highly volatile, just to make you an example. Slide, please. Another challenge was intrinsic, for instance, into the data requirements for microorganisms. I spoke before about the new data requirements entered into force in 2022 on microorganisms, where we give the possibility to applicant to apply for a dossier which doesn't include a single microorganism as an active substance, but as a full consortium. This, of course, gives a lot of advantages in terms of plant protection, because combining different mode of action may trigger less resistance occurring in the field, but of course raises a lot of questions under the risk assessment side, because we need to assess then multiple strains of microbial active substances into the same formulation. There is an ongoing discussion about how addressing this at the best. Slide, please. As regards future perspective of biocontrol in Europe, you know that in February this year, there was a new communication from the Commission called the Vision for Agriculture and Food, where the Commission is basically admitting some bottlenecks of the assessment of the speed as regard access to market of biocontrol, which are, for instance, staying into the risk assessment issue. So we need a faster risk assessment. We need more relevant expert employed in assessing biocontrol, and we need more resources. This is why, slide please, the Commission is committing in providing more resources, for instance, to EFSA, to the European Food Safety Authority, and to improve the regulatory framework to make it more fit for purpose for biocontrol substances. We are in particular discussing about targeted amendment to Regulation 1107/2009, so the regulation concerning access to market of pesticides in general, to include, to give you some example, definition of biocontrol, provisional authorization for biocontrol, or a fast-track procedure for the assessment of biocontrol. Of course, there are a few other ideas which are still under discussion, and 10 minutes I just try to squeeze everything I could say, but I'm open to receive other questions because this was my last slide. Thank you very much.
Perfect. Thank you, Domenico. That was great. Thank you very much indeed. And you can see how to contact Domenico there. So we are running very close to time. So please contact him directly if you have any questions. Just like to invite Antonia onto the stage. Look at that. She just did it herself.
That's how quick it goes. I hope everyone's ready for last presentation of today. Yeah, so welcome. I present the work of the transition work package, not just done by us, but many other colleagues, and especially also thank you to all the case study site leaders and their teams. Overall, we conducted over 30 workshops with them, which is very vital for our results. I wanted to start with a little recap. So why do we even want to transition away from pesticides or from pesticide dependency? These points are not new, but I just thought I'd repeat them again now as we come to the end. So we don't just want to transition because of these environmental and health reasons we heard before, but also because the current system structurally resists change. We see that policy efforts are currently stalling, so previous bold targets are losing its traction right now. We also can kind of see that incremental change is not enough, so replacing works in many cases, but not everywhere. And we're also worried, and we see many results on this, that previous challenges just repeat themselves. And that's why we kind of see that system redesign is needed. And we also saw today that it's actually possible. So the two farmers presenting their work is a positive message, I think. So you can see here our approach for this work package. So we started collecting a lot of input from different stakeholders through different channels to, in the end, or beginning to define the barriers to uptake of alternative practices. These barriers and also the current practices are kind of kept in a lock-in state. Here you can see it kind of visual in this round wall. We started together with stakeholders to define the vision. So how can the future look like when we're not dependent on synthetic pesticides anymore? These visions look very different. In the end, we defined 11 different ones, so 10 for each one for each case study and their specific farming system and regional context. and one general where we kind of summarize it. And yeah, and then we kind of approached this in a backcasting method. So we tried to go backwards from the future vision to the current state and define what is the pathway to get to these visions. So pathway is basically the combination of different actions that needs to happen over time to enable this vision in the future. And yeah, then we all put these results into the current policy landscape and yeah, give recommendations on how to move forward. Yeah, and we wanted to emphasize again that these were all defined in a co-creation effort. So it's based on European stakeholders' input. And when we talk about reducing reliance on synthetic pesticides, the challenge is not just about offering alternatives, but yeah, we should also start to understand why change is so difficult in many cases. And the current system is held by two forces. So you can see the barriers, which before you saw these visible roadblocks, like limited access to alternatives or yeah, doubts about how well they will work. And we also have these lock-ins, so more like deeply and often invisible mechanisms like how success is measured in our economy, but also how research priorities are set. And yeah, these can all then be sorted into these here 6 dimensions on the left. I wanted to just show you one example. So if we zoom into the agronomy and research section, we can see the barrier of even when biological control exists, like we saw from Francisco before, they may not fit with the existing practices or machinery the farmer has in place. So that's a clear barrier. But yeah, the underlying lock-in is that the system depends on these annual yields, so as a success measure. And we also have like a lack of investment generally in alternative knowledge pathways. So the farmer continues using the same products and methods. And yeah, together these forces reinforce each other. And that's why isolated solutions might not actually work in some cases. And this slide illustrates how we approach this visioning process. You can see here the two time horizons used for this. So we see like a more short-term vision that is focused on reducing reliance and managing risks. And on the other side, you see a more long-term vision that targets whole agri-food change. And yeah, in both visions, we see a steady decline in external inputs, paired with a rise in ecosystem services and also farm-level diversification. At the bottom, you see this gray arrow that kind of should symbolize that this is all accompanied by a general decrease in also mineral fertilizers and irrigation, although this wasn't part of our visioning. This is kind of a accompanying aspect. So, as I said, we defined these 11 visions, one per case study site. And we focused on we asked participants to please imagine a desirable future. So first, the more short-term one that goes on the reduction, reliance and risk. So we see that we shift from more like preventive or from curative over preventive methods. And we substitute potentially with biocontrol options where available. And also introduce new crops or varieties. While in the system change, we have we also target other parts of the agri-food chain. So farmers have access to new supply chains. These are potentially fairer, more local, there are policies that ensure fair income for farmers and reduce the corporate influence. And we also have a general society that values ecological resilience and responsibility. We then just quickly move on to the pathways. So remember, these were the steps to actually get to these visions. This was kind of the logic behind. So for each of these dimensions, we defined actions that need to happen in a short term, mid-term, and long term. And we see in the short term, the priority is more on like awareness and initiation by recognizing the risk of pesticide dependency and also surfacing existing alternatives. In the mid-time, we go more to promoting these solutions and also scale them up and make sure that there's enough capacity building to actually introduce new systems. And in the long term, we kind of focus on institutionalization and like a wider system integration. And it also kind of makes sure, or symbolize very well that change doesn't happen all at once. So also it's different for each farm, for each country. So it's very difficult to generalize. We defined this for each farming system that was in the consortium. You will find all of these pathways in our final report, which is coming out soon. And I wanted to give some insight to one of the dimensions for now. So this is on governance, policy, and institutional frameworks. So this is a little bit further away now from the actual farm. So in the short term, we focus on procurement, reduction, and advisory reform. So stakeholders emphasize that they would like to see more national or regional phase-out plans that are specific to the crops grown in their region or country. Also was suggested to introduce a toxicity-weighted tax on existing products. And also, a procurement reform. In some countries, this was really successful already and could also potentially be scaled up for other countries. Also, big emphasis on advisory, so something like a advisory hub that is accessible for practitioners. In the midterm, it's more targets again on like territorial governance and also aligning with rural planning, because fear of losing land or agriculture land was a big topic in all workshops. So something like a decentralized land use planning council that makes sure that pesticide-free or pesticide-reduced production land is actually existent and is also kept, so people have planning certainty. But also something like national agroecology strategies and local food councils. That was something also successful in some countries and could potentially be scaled up. And in the long term, it focused then very much on legal standards and cross-sector governance. So to make sure that different topics like health, agriculture, environment are all thought together. The examples get quite abstract there, so it's not very tangible right now, but we're currently working on for the report to kind of size that down more so that it's more practical. And all of these suggestions kind of exist within a existent policy landscape. So this is just an example. We see we have laws and directives existent, but also many other maybe non-binding, partially binding strategies around it. And for today, we wanted to focus on the common agriculture policy. Simply because it is currently our biggest lever to change land use and agriculture practices. And the newest architecture is already supporting, I think, environmental benefits way better than before. But what we did was analyzing different architectural aspects of the cap to see how they impact a potential reduction of pesticide dependency. So we start here with the conditionality, which is kind of the base of receiving funding in the EU as a farmer. So they consist out of minimum standards that are binding for everyone. So EU rules and or laws, and also national requirements. But then also the so-called GAEC, so minimum standards for farmers to conduct environmental supportive practices. And this applies to nearly all farmers applying for this or applying for funding. So it is a big part. And we see some chances and challenges here. So these different GAECs all support different practices. And there was recently a simplification package introduced. So some of these are proposed to be changed. So some of them, for example, the exception now for organic farmers for some compliance checks, in a couple of them can be seen positive for organic uptake, which is also positive to reducing pesticide use because barely any use in organic. We also see now more increased in this proposal national flexibility in defining some of these standards. So that can be great if it actually applies then better to the national context, but it can also dilute your uniform environmental protection. We also see others, but I'm gonna jump because we're running out of time. Another element are the eco schemes, also well known, I guess, to many of you. They can reach a very wide audience. They usually kind of more short-term commitments, so this can kind of discourage long-term investments in these sustainable practices. And also now with potentially lower GAEC rules, the pressure on them is very high to actually deliver high impact results. And in our analysis, we analyzed how many of the member states actually introduced specific practices in their eco scheme. So based on the JSC farming practice list. And we can see here when we look at them that they vary quite a lot. And if we focus on two of them, we can see that, there's a few more countries actually introduce crop diversification over crop rotation. If we look at the percentage of eco scheme budget that is associated with these, we see a 24% difference. What does that mean in the end? So we see that currently there's like an emphasis on crop diversification, but not necessarily on crop rotation, which could be a challenge because we see that ambitious crop rotation has higher likelihood of actually supporting reducing reliance on pesticides. So our general CAP reflection is that there is a lot of potential right now. There's currently more an emphasis on reducing the use of specific pesticide or limiting its use, which first sounds great, but is actually in daily practice not necessarily very ambitious. It also supports targeted landscape features and promotes organic farming, but there's not so much support yet for crop rotation, mixed cropping, also biological control, and also generally low input systems. And yeah, these simplifications can be a challenge, so it might reduce the key environmental safeguards. So for the future, specifically on the conditionality in eco-schemes, we suggest, based on all of these results and our analysis, that we keep the ambition high for a basic conditionality. We could also integrate IPM practices already in conditionality and complement this then with ambitious eco-schemes that also reward going beyond these guides. And if we now think back to the pathways we presented before, I chose a few policy recommendations that also refer to these actions presented before. We have a long list of policy recommendations, but that would become too long today. But yeah, so we suggest that we should ensure a legally binding pesticide reduction on a country scale, so take into account the different national realities right now. We also should prioritize multi-annual support for these agroecological practices, and potentially also introduce a transition fund that specifically covers these upfront investment costs. We also heard before already, and yeah, ensure that it supports actually all farmers. And additionally, we should assess and update the national agriculture curricula. So potentially EU-wide fit for practice assessment could help national authorities to review their the agriculture curricula. We saw in many workshops that this is, and also in literature, that this is a big issue right now, that these are simply not prepared to help farmers guide the transition. Then we also want to suggest that independent advisory services need to be scaled up. It was also heard before in several presentations that this is a clear lack currently, that we should include this. And the last point, so procurement, I just briefly covered it before, but I think there could be a big chance in going beyond current procurement plans to make sure that also retail and public procurement is up to speed and supports the provision of pesticide-free food. Yeah, this is all. Thank you.
This one, yeah, we're good. Thank you very much, Antonia. Please take a seat. We're going to have our final panel, and our final panel is going to be quick because we do have to go home at some point today. Some of you will be cheering, others of you will be thinking, what? No, I need more sprint in my life. See, Abdullah needs more sprint in his life already. So can I invite up to the stage, please, Just? Max would be great, thank you. Christine, Violette, and Antonio's already here. Excellent. Online, no online person looking, no idea, no, don't know about the online person. Okay, I'm going to assume the online person is not joining us. So please. Oh,
I'm here, in case it's
yes,
me,
please,
Domenico.
please. Oh, brilliant. I was expecting somebody online who turned up in person. Even better. That's great. So as we are pressed for time, so I have some simple questions, and I'd say imagine that we're on the TV and you have to be quick, otherwise they'll change over and show you whatever Donald Trump has just said. So, you know, who knows? So try and be quick. So if we start, let's see, we'll pass you a microphone, would be nice, wouldn't it?
So,
take that one.
First question will be for me.
Yeah. Okay, can you just quickly introduce yourself?
Sure. I'm Aymeric Berling from DG Agri, so European Commission, DG Agriculture. and I'm working particularly on the link between the CAP, the Common Agricultural Policy, and the pesticides regulation. So I think we are in the topic.
Perfect. So what would you say is the most important, most urgent enabler to unlock a transition to sustainable pathways of pest management?
Yes, thank you. I think it's a very important, probably the key question, especially when we look at it from the DG AGRI perspective and the farmer's perspective. I think I was very interested to hear the policy recommendations that you have. And I was very pleased to see that you put emphasis on advice, and it's something that I would like to maybe to insist on, and maybe to briefly explain a bit what the CAP can do, because the CAP can do quite a lot on that. Advice is a key enabler for the farmers to, let's say, to take up the integrated pest management that is a key in the Commission view for the transition towards sustainable use of pesticides. And the CAP has an instrument which is called the Farm Advisory Services, which actually requires, it's an obligation for national authorities to make available advice to farmers on a list of topics, and this list includes IPM and the sustainable use of pesticides. So it's an obligation. So I was very pleased to hear that it's one of your policy recommendations. There is already a good start, if you want, in the CAP. And further to that, there is a possibility of financing. You mentioned the budget of the CAP, which is significant. And I think with this budget, we can do quite a lot because we are dealing with farming practices. And the CAP can finance the advisory services. So, for instance, the use by farmers, if the advice is charged, or the setting up of that. So there are quite a lot of possibilities. And without saying, of course, the list of instruments in the green architecture that you have mentioned, to which I would also add the collective approaches, which are important, in particular in certain sectors, which are very, I would say, sensitive for the use of pesticides, fruit and veg, wine. For that, the eco schemes, etc., have a little to grasp, because these are not sectors which are particularly attracting this part of the budget. But for that, we have collective approaches through operational programs. And then maybe I will stop here because I understand that maybe.
Perfect. Thank you. Shall we pass over to Max, who's been waiting patiently since lunchtime, I think?
Thank you.
Do you want to introduce yourself and just say what you think would be the most urgent enabler to unlock a sustainable pesticide pathway?
Yes, very good. I think that's a very, very good and very important question. So my name is Max Schulman. I'm an arable farmer from Finland. I'm working as an advisor for the Finnish farmers in Finland as a senior advisor on cereals, oilseed, protein crops. And also then here in Kopa-Koshika, I'm chairing the phytosanitary working group, mainly handling then their plant protection products and also plant health issues as well. So the toolbox is something that I'm always interested in. But you asked, what would be an enabler? And I think that one of the first things that I would say is that we need to have an access to the new biocontrol. We don't have that today. In many, many countries and for many sectors, there are not any or very few biocontrol products on the market. So that's one of the first things that we would need to make sure that we will have these on the market so that the farmers can really go in and use them, try them out on their own farm, try how they fit into our crop rotation that we have there, and see then what kind of changes we have to make and how they fit in to the toolbox of the plant protection products we have today with the synthetic ones. So they will always be working there together. But today we have a lack of these products on the market. So actually I would say what would be needed is a mutual recognition system, whereas EFSA would have been able to make sure that we have the active substance recognized, it has been approved. Then when it comes down to the member states to be able to make sure that we will have the product on the market, there we should have a full 100% EU-wide mutual recognition without zones, so that we would be able to get faster access to to these products. I'll start with that, and I will stop here.
Perfect. Do you want to hand to just Christine? Christine, introduce yourself.
Yes, thank you. My name is Christine Schamfelare. I work as policy officer for Pesticide Action Network Europe. Maybe I want to start with thanking quickly the Sprint project for this conference today and the very impressive amount of work that has been done, which is very valuable. Maybe, yeah, I think there are different key enablers necessary, but I think I would start by saying that the current Sustainable Use of Pesticides Directive, which has also been highlighted today, that is really key. It's good implementation, it's good in transposition into national law, because, for example, integrated pest management, which really should ensure that the least harmful practices, the practices least disruptive to agro ecosystems with the lowest risk to environment and health, should be implemented. That is mandatory by EU law since 2014, and this has not been happening. So this implementation and enforcement of this directive is key. And then one of the aspects to practically foster that is what has also been named already. I think it's key to have these independent advisory systems really widely available to farmers, because we notice that if that is the case, for example, in projects as IPM works, which have been really successful, but there are many examples throughout Europe of successful practices which greatly reduce or completely phase out pesticide use while maintaining robust yields. These are clear that when these independent advisory systems working with bringing together scientists, advisors, farmers, and also, for example, fostering peer-to-peer learning, that this really works. So I think if every farmer would have access to this, it would be a game changer. And we also hear this frequently from farmers themselves, who also say they lack now the high expertise advice on IPM, and who even say they often receive messages or recommendations to spray when they themselves, for example, don't think it's needed. So it's really also a big demand we hear from farmers. Thank you very much.
Thank you. Joost?
Yes, hello. My name is Joost Vlaming. I'm part of Sprint project representing FAO. I'm working for the FAO Pest and Pesticide Management Group that focuses on reducing the reliance on chemical pesticides. I'm mostly involved not in working directly with farmers, but rather with the registration authorities, registrars, and we are aiming to build capacity among registration agencies in low and medium income countries. We all know how complicated this field is, and then if you imagine the number of people working on this topic in Europe alone in the different countries, but also shared in Europe, and then comparing that to maybe a handful of people working on registration in low, medium income countries, you can imagine how difficult it is for them to make similar quality level decisions. So for me, from that point of view, it's really about resources, resources in number of people, but also in specialization and time available, even money available to be able to do certain laboratory tests and so on. Policy is really a thing. We see places where there is actually no updated policy framework, so whatever they have to work with might be quite outdated. And then I think it was also mentioned here, sharing information among its member states in Europe, but in low, medium income countries, there's a desire for autonomy. So there are very few countries actually joining hands, working together on these registration decisions. West Africa is an example where they do share registration, but many other countries, it's just each of them repeating the same kind of work. And so there's a lot to gain in order to enable those registrars, which are gatekeepers that can keep products off the national markets. So,
perfect, thank you. Antonia, do you want a quick word about the key enabler?
I think, yeah, I can agree with everything that was said. Something that wasn't in the presentation before, but is also really relevant, is the idea of cognitive and social norms. So I think without consumers, but also farmers and everyone else in the food value chain, without them realizing that there's a change needed and there are also options for this, I think all these other options are not falling on fertile ground. So I think we need to make sure that we have informed consumers that all of this data that was also presented today is actually available to people. I think the presentations were great, but maybe people need to also see them in a different format to also understand them. So I think, information is key here to also change mindsets of people. And this probably costs a lot of money and also effort. But I think we saw on completely different topics before that this is actually possible to change people's mindsets.
Perfect, thank you. Now, I've been teasing her all afternoon by not letting her speak. So the boss of the project, Violette, who's led us for 5 years, gets to say the final few quick words. So Violette, what would be the key enabler to unlock this change?
The key for me for change as an agronomist would be, I fully agree with Max, make biocontrol pesticides, or how you would call them, available for the market, and go very fast to make these procedures happen, to make them have regulated. This is the base. The next thing is give farmers in all national countries, in all member states, in the education, an agroecological education. I like these presentations here of our farmers who were here. They had tenías capacitaciones y todo eso, no? They had capacity building to know how they can fight against pest diseases. So a lot of educations from farmers nowadays is only based on one side of the coin. And I think it would be very good to make an integral education for the farmers. And the next step is farmers are often accused, you do all these bad things, you apply these pesticides. That is not fair, because farmers apply pesticides which are approved by the EFSA. So they are meant to be saved and sold to be safe. Farmers themselves are not informed that if they apply 20 pesticides in a growing season, or that they mix pesticides, what is the risk for themselves? So I think it would be very important that the EFSA regulations in a very short term includes the safety approvals for all pesticides which are recommended to be sprayed on one crop. I think that is as well a very important issue. And the next issue is that I think these examples from our farmers here showed very well, if you can find solutions, you can find really options how to deal with, but then you need really knowledge. And I think the knowledge is there, and I really appreciate if you say from the European Commission, CAP will make it possible to give farmers knowledge, more knowledge about sustainable use, and if the EFSA would make these approval procedures in a very short term onto the market so that farmers can choose. And yeah, that were my words.
Perfect. Thank you very much. Now, I appreciate that's a really quick panel, but we have nearly run out of time. So I would like to thank everybody on this panel. Lovely to see people who might otherwise we would think disagree, agreeing, which is always a lovely thing to see. So thank you for that. Thank you very much for turning up today. I appreciate all the work that you've done and also your participation today. So a big hand for our panel, please.
And before you leave, just some words for my part.
Yeah.
Well, so thanks all for being here. And I have to say, I really loved this project. I never in my life had so much challenges in a project and so much fun on both sides. No, and I learned so much, and it was a great team, and I really appreciate that we did everything together with so many views of the world. And coming together, it was really a pleasure. Luckily, we have still half a year to follow up with dissemination, and maybe we will approach one of the others of you to tell us what you think, how our information should be disseminated and could be used to be implemented in the future. And Vera, you have something? Because we wanted to thank a lot. Thanks to Matt.
Oh.
No, but this you can do. No, no.
Oh, you're very kind.
For Matt and Jane for all these preparations. It's only a little bit from Belgium. So thanks a lot for all the work University of Gloucestershire, now I can pronounce it well, have done. And thanks you all. And please don't hesitate to contact us via sprint@vuur.nl for every questions you have, comments, ideas. Please stay with us, stay connected. And we hope that we as well can, when the sprint project is finally over, find a place where we can place a toolbox visible maybe from the European Commission, that we get a space to post it there, that it will be for the rest of the European life there available. Thanks a lot again.
Thank
and
you.
have a good journey home.
I know you've been waiting for the winner of the poster competition all day. So Erin, would you like to stand up? Or has she left already? No. Okay, no, I don't want this to change your life. I don't want your friends to say she was such a nice woman until she won this prize and it turned her head and she went strange. So a special sprint mug with some chocolates. Well done. Thank you very much. And thank you everybody for your participation today. You've been great. Thank you.